Hello, and welcome to Sleepy Science. What if mathematics is not just something we use to explain reality, but the hidden code reality has been following all along? What if a chessboard contains more possible futures than the atoms in the universe? Randomness has secret laws. Infinity has larger and smaller forms. And nature builds trees, lungs, rivers, clouds, spots, stripes, and galaxies through patterns your eyes feel before your mind understands. In this journey, we'll explore the strange mathematics hiding beneath everyday reality. From chaos and probability to fractals, networks, entropy, algorithms, and the impossible structures we cannot even visualize. These are not school equations. These are the hidden rules shaping nature, information, beauty, and the universe itself. So tap like, hit subscribe, and step into the mystery with me, because the deeper we look into mathematics, the more reality starts to feel like a language we were born inside, but never learned to read. There are more possible chess games than atoms in the universe. A chessboard looks like a small battlefield, but hidden inside its 64 squares is a universe so vast that the stars feel almost countable beside it. At first, chess seems contained. You can see every piece. You can learn every legal move. Nothing is moving faster than your eyes can follow. There are no hidden cards, no dice, no random storm entering the board from outside. Two players sit across from each other, and everything that happens must happen through rules simple enough to teach a child. But the moment the first move is made, the board begins to open. Each choice creates replies. Each reply creates new replies. After only a few turns, the game is no longer one road, but a branching forest of possible futures. And as the moves continue, the number of possible games grows so quickly that ordinary imagination breaks. A famous rough estimate, often called the Shannon number after Claude Shannon, suggests that the number of possible chess games is around 1, followed by 120 zeros. The number of atoms in the observable universe is usually estimated around 1, followed by 80 zeros. These numbers are not exact counts carved into stone. They are estimates, and the true number depends on how you define possible games, how long games are allowed to continue, and how repeated positions or draws are treated. But the main truth remains astonishing. The space of possible chess games is so enormous that it can reasonably be compared to, and often said to exceed, the number of atoms in the observable universe. That means a board you can hold in your hands contains more possible stories than matter itself seems to offer in the visible cosmos. And the reason is not magic, it is branching. On a typical turn, a player may have many legal moves. Some are strong, some are weak, some are obvious, some are disastrous. Some look quiet but change everything later. Each move does not merely change the board, it multiplies the future. If you had only 30 choices, and then your opponent had 30 choices, and then you had 30 again, the number of possible paths would explode after only a handful of turns. Chess is not huge because the board is large. Chess is huge because decision follows decision, and every decision opens a new set of possible worlds. This is why no human can truly see all of chess. Even the greatest grandmasters are not exploring every possible path. They are filtering. They recognize patterns, threats, weaknesses, pawn structures, king safety, open files, trapped pieces, long-term pressure, and tactical danger. They survive the vastness by knowing where not to look. Modern chess engines do something similar in a more mechanical and powerful way. They calculate deeply, but they also evaluate and prune. They do not simply list the entire universe of chess from beginning to end. That would be hopelessly large. Instead, they search intelligently, guided by evaluation, training, and probability of usefulness. This teaches a deeper lesson about intelligence itself. Being smart does not always mean seeing everything. Sometimes it means ignoring almost everything and focusing on the few paths that matter. The board becomes a mirror for decision-making in life. You never see every possible future either. You never know every consequence of one sentence, one refusal, one risk, one delay, one apology, one mischance, one act of courage. You stand inside a position created by previous moves, and you must choose without seeing the whole tree. Chess makes that condition visible. A beginner may see pieces. A master sees relationships. A beginner asks, "What can I move?" A master asks, "What does this move make possible, and what does it leave behind?" That is where the game becomes more than a game. It teaches that complexity can arise from clarity. The rules are fixed, yet the outcomes are almost endlessly varied. The pieces are limited, yet the possibilities feel cosmic. There is also a strange humility in this. A tiny mistake in chess can remain quiet for several moves before it becomes fatal. A small pawn move can weaken a square that later becomes an invasion point. A sacrifice can look reckless, then reveal that it was the beginning of a forced attack. The meaning of a move is not always visible when it is made. It unfolds through time. And this is why chess feels so close to thought itself. The board does not reward only calculation. It rewards patience, restraint, memory, imagination, and the ability to live with uncertainty. It is a finite object that produces an almost unthinkable landscape. It shows that vastness does not always require physical size. A brain fits inside a skull and can imagine the universe. A melody lasts a few minutes and can stay with someone for life. A chessboard sits on a table and contains a number of possible futures beyond cosmic intuition. So when you hear that there are more possible chess games than atoms in the universe, do not treat it as only a shocking fact. Treat it as a doorway. It reveals how quickly possibility grows when choices interact. It shows why prediction becomes difficult even in a world with clear rules. It reminds you that small systems can contain enormous depth, and that the visible size of something tells you almost nothing about the hidden space inside it. The chessboard is not large, but its future is. It is silent, but full of storms. It is limited, but never exhausted. And maybe that is the quiet reason chess has survived for centuries. Every game begins from the same starting position, yet no two serious journeys through it need to be the same. The pieces wait in perfect order. But beneath that order is a universe of almost impossible branching, asking one simple question again and again: what will you choose next? Some infinities are bigger than other infinities. Infinity seems like the kind of word that should mean the end of all comparison. The final room where counting collapses and every number becomes equally unreachable. But mathematics hides a stranger truth inside that word. Some infinities are larger than others, not in the casual way one mountain is larger than another, but in a deep and exact way that forces your mind to separate endless from the same size. At first, this feels impossible. If something never ends, how can another thing be more endless? If you can count forever in one direction, what could possibly be beyond that? And yet, this is one of the most beautiful shocks in modern mathematics, because it shows that infinity is not a single ocean, but a whole landscape of oceans, some shallow enough to cross in a strange kind of order, others so vast that no counting process could ever touch every point. To feel this gently, begin with the ordinary counting numbers: 1, 2, 3, 4, 5, and onward without stopping. You never reach a final number. There is always another step. Now think of only the even numbers: 2, 4, 6, 8, 10, and onward. Your first instinct may say the even numbers must be fewer, because they leave out half the counting numbers. They skip all the odd ones. They look thinner, more spread out, less complete. But here the first door opens. You compare every counting number with one even number: 1 with 2, 2 with 4, 3 with 6, 4 with 8, and so on forever. Nothing is left unpaired on either side. Every counting number has a partner, and every even number is reached. So even though the even numbers seem like only half the whole set, they are the same size of infinity as the counting numbers. This is where your everyday sense of quantity begins to bend. In the finite world, if you remove half of something, it becomes smaller. Half a loaf is smaller than a loaf. Half a road is shorter than a road. But infinity does not behave like a loaf or a road. It can lose what looks like half of itself and still remain just as large. That does not mean mathematics is lying. It means your intuition was trained in a world of small, finished things. and infinity does not live by those habits. Now take another step. Think of all the fractions, all the numbers that sit between whole numbers. 1/2, 2/3, 5/7, and endless others. At first, fractions look much more crowded than counting numbers. Between 1 and 2, there are infinitely many fractions. Between any two fractions, there is another fraction. It seems like dust packed between every tile of reality. Surely this infinity must be bigger. But surprisingly, fractions can still be arranged in a careful order, so that if you were patient enough and immortal enough, you could list them one by one without missing any. The order would not be simple like counting straight forward, but it can be done. That means fractions belong to the same broad size of infinity as the counting numbers. They are endless, yes, but they are countably endless. You could imagine them as a library with infinitely many books, but with a system that lets you assign each book a number on an endless shelf. However strange the shelf becomes, every book eventually gets a place. And then come the real numbers, the numbers that include not only whole numbers and fractions, but decimals that go on forever without repeating, numbers that can describe smooth positions on a line, numbers that fill every tiny gap so completely that the line stops feeling like beads and starts feeling like mist. Here the story changes. The numbers between 0 and 1 alone are too many to be counted in the same way. Even that tiny interval, smaller than the distance between two neighboring whole numbers, contains an infinity larger than the infinity of counting numbers. This sounds almost unreal. The space between 0 and 1 holds more numerical possibility than the endless march of 1, 2, 3, 4, and forever. The proof, discovered by Georg Cantor, is one of the most quietly powerful ideas in mathematics. Imagine someone claims they have written a complete endless list of all the decimal numbers between 0 and 1. The list goes on forever. There is a first decimal, a second decimal, a third decimal, and so on. At first, it seems possible that an endless list could contain them all. But Cantor showed how to create a new decimal that is guaranteed not to appear anywhere on that list. You look at the first digit of the first number and choose a different digit. Then the second digit of the second number and choose a different digit. Then the third digit of the third number and choose a different digit. You continue this way forever, changing one digit from each listed number. The new decimal you create differs from the first number in at least one place, differs from the second number in at least one place, differs from the third number in at least one place, and so on. Because it differs from every number on the list, it was not on the list. And this means the original list was incomplete. No matter how anyone tries to list all those decimals, a missing one can always be made. Not because the list was poorly written, but because this kind of infinity cannot be captured by counting. It slips away from every net. It is not merely endless, it is uncountably endless. And when you understand that, even a simple number line begins to feel haunted. Between 0 and 1 is not emptiness. It is not a narrow hallway. It is a universe of values so dense that counting cannot pass through it. You can point to one location, then another, forever, and still you have barely touched the surface. The line is not made of a manageable row of points. It is more like a silence so full that no list can exhaust it. This does not mean every infinity is mysterious in the same way. Some infinities are structured enough to be counted step by step. Others are too continuous, too rich, too tightly filled to ever be placed into a single sequence. That distinction changed mathematics, but it also changes something in the imagination. It teaches you that more does not always mean physically larger. A tiny interval can contain an infinity deeper than an endless staircase. A quiet line on paper can hold more points than there are numbers you could count forever. The small can be larger than the vast, if the small contains a different kind of endlessness. This is why infinity is not just a mathematical curiosity. It is a lesson in humility. Your mind wants the world to fit into familiar categories, bigger and smaller, full and empty, many and few. But mathematics keeps revealing that reality has levels beneath your first impression. Some things that look crowded can be counted. Some things that look narrow cannot. Some forms of endlessness are tame enough to line up like travelers at a gate. Others are so vast, They cannot even be placed in order without something escaping. And perhaps this is why the idea feels strangely emotional. It reminds you that not all unknowns are equal. Some questions can be answered with enough time. Others open into depths where time itself is not enough. Some mysteries are long roads. Others are bottomless skies. Cantor's discovery was not just that infinity exists, but that infinity has architecture. It has layers. It has hidden rooms. It has doors behind doors. And once you see that, the word infinite no longer feels like an ending. It feels like a beginning. So the next time you hear someone say something is endless, pause for a moment. Ask what kind of endlessness it is. Is it the kind you could walk through step by step forever? Always moving, but always following a path? Or is it the kind that surrounds every step with more depth than counting can ever reach? Mathematics does not make infinity smaller by studying it. It makes infinity more alive. It shows you that even the idea of forever has shades, distances, and hidden magnitudes. And maybe that is the quiet wonder. The universe is not only strange because it is large, but because even the smallest spaces inside thought can contain forms of vastness your imagination has not yet learned how to hold. A simple equation can create chaos. The most unsettling kind of disorder is not born from pure randomness, but from rules so clear that they should feel safe. You expect chaos to come from noise, from accidents, from things breaking apart without reason, but one of the strangest discoveries in mathematics and science is that chaos can grow from simplicity itself. A short rule, repeated again and again, can begin with perfect obedience and still lead to behavior so tangled that no human mind can fully predict it far into the future. This is the heart of chaos theory. Not that the universe is lawless, but that laws can produce outcomes too sensitive to follow forever. Imagine placing a drop of ink into water. At first, it seems easy to describe. The ink spreads, the water moves, but soon thin curls appear, folding into smaller curls, stretching, twisting, dividing, and blending until the pattern becomes almost impossible to reverse in your mind. Nothing magical happened. No invisible hand created the complexity. The liquid simply followed physical rules. Yet those rules created a pattern that looked alive. Chaos often works like that. It does not need a complicated beginning. It needs feedback, repetition, and sensitivity. A tiny difference at the start becomes a larger difference later, and then that larger difference becomes larger still, until two situations that once looked almost identical become completely different worlds. This is why the famous butterfly effect is often misunderstood. It does not mean that one butterfly literally guarantees a storm somewhere else. It means that in certain systems, very small changes can grow into very large differences over time. The idea became famous through the work of Edward Lorenz, a meteorologist who studied weather using computer models in the early 1960s. He once restarted a weather simulation using numbers that were rounded slightly differently from the original run, expecting almost the same result. Instead, after enough simulated time passed, the weather pattern diverged dramatically. The machine had not made a mistake. It had revealed something deep. Weather is not difficult to predict only because we lack effort. It is difficult because the atmosphere is a chaotic system. Air pressure, heat, wind, moisture, sunlight, and rotation all interact in loops. A small uncertainty does not stay small. It spreads through the system like a whisper becoming an avalanche. This is why weather forecasts can be useful for the next few days, but become much less reliable farther ahead. The rules are real. The science is real, but exact long-term prediction becomes impossible because no measurement of the present can be perfectly complete. You can know a great deal and still not know enough. That is the humbling part. Chaos is not ignorance alone. It is the discovery that even perfect rules do not always give you practical certainty. Think of a simple swinging pendulum. One pendulum moving back and forth is usually predictable, but attach another pendulum to the end of the first, and suddenly the motion can become wild, flipping and looping in ways that seem almost emotional. The device is still obeying physics. It has not become random, but its motion is so sensitive to tiny differences that watching it feels like watching order lose its balance. The The same kind of lesson appears in dripping faucets, turbulent rivers, electrical circuits, traffic jams, population changes in nature, and even the rhythms of the human body. A heartbeat, for example, is not perfectly mechanical like a clock. Healthy biological rhythms often contain subtle variation, a flexible kind of order that helps the body adapt. Too much rigid regularity can sometimes be a warning sign, while too much irregularity can become dangerous. Life does not always live at the extreme of order or the extreme of disorder. It often lives near the border, where patterns are stable enough to hold together, but flexible enough to respond. That border is where chaos becomes more than a mathematical idea. It becomes a way to understand why the world feels both lawful and unpredictable at the same time. You can see it in how a crowd moves through a narrow exit, how a rumor spreads through a city, how a small delay in traffic can grow into a long line of braking cars, even when there is no accident ahead. Each driver reacts to the car in front of them. Each reaction is small, but the reactions feed into one another, and soon a wave of slowing travels backward through the road like an invisible pulse. No one planned the jam. No single person caused the whole pattern. It emerged. That word matters. Emergence is what happens when many small interactions create a larger behavior that was not obvious from the pieces alone. A simple equation, a simple rule, a simple feedback loop can create something that feels richer than its ingredients. And this is where chaos becomes quietly philosophical. You may want life to be predictable if you do the right things, avoid the wrong things, and understand the rules. But the world is not a straight machine that always gives simple outputs from simple inputs. It is full of systems where tiny moments matter more than they appear to. A conversation can change direction because of one word. A habit can grow from one repeated action. A fear can become stronger because it is rehearsed. A small act of kindness can travel through people you never meet. This does not mean everything is out of control. It means control is more delicate than we like to believe. Chaos teaches that the future is not always hidden because it is mystical. Sometimes it is hidden because the present is too detailed to capture completely. There are too many small conditions, too many quiet interactions, too many invisible beginnings, and yet this should not make you feel powerless. In a chaotic system, small things can matter. Not always in ways you can predict, not always in ways you can command, but they are not meaningless. A slight change in direction, repeated over time, can become a different path. A small correction early can prevent a larger collapse later. A gentle influence, placed at the right moment, can reshape the flow. That is why chaos is not only frightening, it is also strangely hopeful. It says the world is sensitive, not dead. Responsive, not fixed, alive with consequences that move beneath the surface. The same science that limits prediction also makes transformation possible. If everything were rigid, nothing small would matter. If everything were random, nothing intentional would matter. But chaos lives between those extremes. It gives you a world where rules exist, yet surprise survives, where patterns form, yet certainty fades, where a simple beginning can unfold into astonishing depth. So when you hear that a simple equation can create chaos, do not imagine mathematics destroying order. Imagine order revealing how deep it really is. Imagine a quiet rule repeating in the dark, folding the future again and again until a shape appears that no one expected. And maybe, as you listen to that idea, you can feel something familiar inside it. The way your own life has never been purely random, yet never fully predictable. The way small moments have quietly redirected you. The way a simple choice can echo farther than you know. Chaos is not the absence of meaning. It is the reminder that meaning can grow from the smallest rules, the smallest changes, the smallest beginnings, until the world becomes too rich to ever be completely held in the hand. Random data often follows hidden laws. A pile of scattered numbers can look like pure noise until you step back far enough to see that the noise has a shape. At first, random data feels like the opposite of order. It feels like dice rolling, coins flipping, footsteps crossing a busy street, raindrops striking a window, people choosing different doors, different words, different times to wake up, different routes through a city. Each single event can seem unpredictable, almost private in its disorder. You cannot know with certainty whether one coin toss will land heads or tails. You cannot know exactly when one customer will enter a shop, which raindrop will hit the glass first, or how one tiny particle of dust will drift in the air. But when these events gather in large numbers, something strange begins to happen. The individual moments remain uncertain, yet the crowd begins to obey patterns. Randomness, when seen one piece at a time, looks wild. Randomness, when seen in thousands or millions of pieces, often becomes surprisingly disciplined. This is one of the quiet miracles of statistics. Disorder at the small scale can become order at the large scale. A casino does not know whether one player will win one hand, but it can estimate what will happen across thousands of games. An insurance company does not know exactly which one person will have an accident this year, but it can predict risk across a population. A scientist cannot predict the exact movement of one molecule in a gas, but can describe the temperature and pressure of the whole gas with great accuracy. This does not mean the randomness was fake. It means randomness has laws of its own, not laws that tell you every single detail, but laws that describe the shape of the whole. Think of flipping a coin. If you flip it only 4 times, you might get heads every time, and nothing about that small result feels balanced. If you flip it 20 times, the result may still lean one way. But if you flip it thousands and thousands of times, the proportion usually drifts closer to balance. Not because the coin remembers, not because the universe is correcting itself, but because large numbers smooth out the accidents of small samples. This is an important lesson. Randomness can look misleading when you only see a tiny piece of it. A short streak can feel like destiny. A few coincidences can feel like a hidden message. A sudden cluster can feel meaningful even when it may simply be part of how randomness behaves. Human minds are naturally hungry for pattern. You see faces in clouds, intention in silence, signs in repetition, meaning in timing. This ability helps you survive because patterns can matter, but it can also fool you because random data is not evenly spread in the way people expect. Real randomness often creates clumps, streaks, gaps, and surprises. If you look at a truly random sequence, it may not look random enough to your intuition, because your intuition expects randomness to be neat, balanced, and fair in every small section. But true randomness is allowed to be messy. It can repeat, it can bunch together, it can create strange-looking runs that seem designed, even when no design is present. This is why people can believe a basketball player is due to miss after several successful shots, or that a number is due to appear after being absent for a long time, even when the process has no memory. In many random systems, the past does not force the next event to balance the story. The next coin toss does not know what happened before. The dice do not feel guilt. The universe is not always trying to make small samples look fair. And yet, when enough events accumulate, the larger pattern becomes reliable. This is not a contradiction. It is the difference between predicting an individual and understanding a population. The same principle appears in the natural world. Radioactive atoms decay unpredictably one by one. You cannot point to one unstable atom and say exactly when it will change. But if you have a large amount of that material, scientists can predict the rate at which many atoms will decay with extraordinary precision. The single atom is uncertain. The group has a pattern. In medicine, one person's response to a treatment can vary, but across many people, researchers can detect whether a treatment tends to help, harm, or do nothing. In cities, one person's movement may seem personal and spontaneous, but traffic flow, pedestrian timing, and public transport use often reveal patterns when measured at scale. Even the background noise of everyday life, purchases, clicks, delays, arrivals, waiting times, can form recognizable shapes. This is why data can be powerful and also dangerous. It can reveal hidden regularities that no single person could see, but it can also tempt people to overread patterns where the evidence is weak. A cluster is not always a cause. A trend is not always a truth. A correlation is not always a story. To understand random data, you need patience, context, and humility. You need to ask not only what pattern do I see, but could this pattern appear by chance? That question is one of the foundations of scientific thinking. It protects you from superstition, from false certainty, from turning noise into prophecy. But it also opens your eyes to real hidden structure. Because some patterns are not illusions, some patterns are signals buried under randomness. And learning to separate signal from noise is one of the most important skills in science, business, medicine, and daily judgment. Weather measurements, election polls, medical trials, quality control in factories, search engines, financial risk models, and even the way streaming platforms recommend videos all depend on finding patterns inside messy data. The world is too complex to understand one event at a time, so we collect many events and let the larger shape speak. Still, there is something deeply human in this. Your life often feels like a series of isolated moments. One good day, one bad message, one mistake, one lucky break, one rejection, one unexpected kindness. If you judge everything from a tiny sample, you can easily misunderstand the whole. A bad week can feel like a doomed life. A lucky streak can feel like permanent protection. A few failures can feel like proof that nothing will ever change. But random variation exists in human experience too. Not every rise is destiny. Not every fall is identity. Some moments are noise, some are signals. Wisdom is learning to tell the difference slowly, without panic. Random data teaches that the world is not always readable from the nearest detail. You often need distance. You need more evidence. You need time. And when you step back, what looked like meaningless scatter may begin to reveal a curve, a rhythm, a tendency, a quiet law hiding beneath the surface. That is the strange beauty of randomness. It does not destroy order. It often becomes the material from which a deeper order can be discovered. So when you hear that random data often follows hidden laws, do not imagine that chance is an illusion or that everything is secretly controlled. Imagine something subtler and more powerful. Imagine a world where single events can remain uncertain while the whole still carries structure. Imagine raindrops on glass, each landing unpredictably, yet together tracing the direction of the wind. Imagine human choices, each personal and imperfect, yet together revealing the pulse of a city. Imagine noise not as emptiness, but as a veil thin enough for careful minds to see through. And maybe the next time life feels scattered, you will pause before calling it meaningless. Because sometimes the pattern is not absent. Sometimes you are simply standing too close to see it. The first digit is not random in real-world numbers. The first digit of a number seems like the last place you would expect nature to leave a fingerprint. Yet in real-world data, the number at the front is often not as random as it looks. Open a table of city populations, river lengths, electricity bills, stock prices, building heights, earthquake measurements, company revenues, scientific constants, or the sizes of files on a computer, and something quietly strange begins to appear. Numbers beginning with 1 often show up far more than numbers beginning with 9. Not a little more. In many naturally occurring datasets, the leading digit 1 appears around 30% of the time, while 9 appears much less often. At first this feels wrong. If the first digit can be 1, 2, 3, 4, 5, 6, 7, 8, or 9, your intuition expects them to appear evenly, almost like names pulled from a hat. But the world does not always distribute numbers the way intuition expects. The first digit is not a coin toss. It is often shaped by growth, scale, and the hidden way quantities spread across many sizes. This pattern is commonly known as Benford's law, named after physicist Frank Benford, though the astronomer Simon Newcomb noticed the idea decades earlier when he saw that books of logarithm tables had more worn pages near the numbers beginning with 1. That tiny observation was almost poetic. Human hands had touched some number pages more than others, and the wear on paper hinted at a hidden imbalance in reality. Later, Benford tested the pattern across many kinds of data and found the same uneven rhythm appearing again and again. But this is not magic, and it is not a rule that applies to every list of numbers. It works best when the data comes from real processes that stretch across many different sizes, rather than from numbers humans assign artificially. Phone numbers do not have to follow it. Lottery numbers do not have to follow it. A list of people's ages in one school will not follow it well, because the range is too narrow. But when numbers grow, shrink, multiply, divide, spread across scales, and arise from the messy machinery of the real world, the first digit begins to lean towards smaller numbers. The reason is simpler and deeper than it first sounds. Think of a quantity growing over time, such as a town's population, a company's income, or bacteria in a dish. When a number begins with 1, it has a long journey before the first digit changes. A population of 1,000 must grow all the way to 2,000 before the first digit stops being 1. That is a doubling, but a population beginning with 9, say 9,000, only needs to reach 10,000 before the leading digit changes back to 1 again. That is a much shorter relative step. So growing quantities spend more time, in a proportional sense, wearing the face of 1 than wearing the face of 9. The same idea appears whenever numbers move by percentages rather than by equal steps. Much of the real world grows by proportions. Interest grows by percentages. Populations increase by rates. Businesses expand by ratios. Natural measurements often spread over wide ranges. A river can be a few kilometers long or thousands of kilometers long. A city can have thousands of people or tens of millions. A company can earn a little or an enormous amount. When quantities live across these wide ranges, smaller leading digits naturally take up more room in the hidden scale of the data. The digit 1 is not being favored by chance. It is being favored by the structure of growth itself. And once you understand this, ordinary tables of numbers start to feel less ordinary. A spreadsheet becomes a landscape. A column of figures becomes a kind of fossil record, preserving the way things expanded, accumulated, and spread. You begin to see that numbers are not always dead labels attached to reality after the fact. Sometimes they carry the shape of the process that created them. A mountain height, a bank balance, a scientific measurement, a country's population. Each number seems individual, but when gathered with others, the leading digits may reveal the quiet signature of scale. That is the beautiful part. The pattern does not require the numbers to be related in an obvious way. You can mix data from different domains, and if the values cover several levels of size and are not artificially restricted, the same first digit imbalance can appear. It is as if the world, when allowed to range freely from small to large, naturally spends more time near beginnings than endings. But this pattern must be handled carefully. It is not a universal test of truth. Real datasets can fail to follow it for good reasons. Prices in a store may cluster around psychological endings. Human-designed identification numbers may be assigned in controlled ways. Measurements with strict minimums and maximums may not have enough room to reveal the pattern. Data that has been rounded, filtered, capped, or collected from a narrow category may behave differently. This matters because the law is powerful only when used with understanding. It can help auditors, scientists, and investigators notice suspicious data sets, because fabricated numbers often fail to match the natural first-digit pattern. People inventing figures tend to spread first digits too evenly because they assume randomness should look balanced. But real-world numbers often do not look balanced. They look tilted. And that tilt can expose the difference between organic data and artificial imagination. Still, Benford's law is not a judge by itself. It cannot prove fraud alone. It is more like a smoke alarm. It says, look closer. It points toward places where numbers may deserve attention. And that alone is fascinating, because it means a small detail, the first digit, can become a doorway into trust, evidence, and hidden behavior. Something as simple as whether a number starts with 1 or 9 can help reveal whether a dataset breathes like reality or feels too neatly invented. But beyond accounting and analysis, there is a quieter lesson here. Your mind expects fairness in places where the world has structure. You see 9 possible leading digits and assume they should share the stage equally. But equality of options does not guarantee equality of appearance. The world is shaped by processes, not just possibilities. Some outcomes have more room to occur. Some states last longer. Some patterns appear often, not because they are chosen, but because the path of reality passes through them more frequently. This is the difference between looking at the surface and understanding the system underneath. The surface says there are 9 digits, so each should appear about the same. The system says growth changes the story. Scale changes the story. The journey from 1 to 2 is not the same kind of journey as the journey from 9 to 10. And once you notice that, the idea becomes strangely philosophical. How many times do you expect life to be evenly distributed just because the options seem equal? How often do you mistake imbalance for unfairness when it may be the result of hidden structure? How often do you assume that chance should look smooth when real processes produce slopes, clusters, and quiet preferences? The first digit teaches a kind of humility. It reminds you that reality often carries patterns too subtle for the eye, but too consistent to ignore. It asks you to distrust the first impression, not because the first impression is always wrong, but because the first impression is incomplete. A number is not just a number. Sometimes it is a footprint. Sometimes it tells you how something grew, how wide the range is, how naturally the data formed, or how artificial it may be. So the next time you see a long column of figures, imagine that each one is wearing a mask, and the first digit is the edge of that mask catching the light. Most people pass over it without thinking, but hidden there may be one of the world's quietest laws. Not loud, not dramatic, not obvious, but patient enough to appear in populations, rivers, incomes, measurements, and records across the planet. The first digit is not always random. Sometimes it is the whisper of scale itself, reminding you that beneath the apparent mess of numbers, reality often has a rhythm, and the smallest beginning can reveal the shape of the whole. A coastline gets longer the closer you measure it. A coastline is one of those things that looks settled from far away, as if nature has drawn a clear border between land and sea, but the closer you move toward it, the more that border begins to misbehave. From an airplane, the edge of an island may seem smooth, almost like a single graceful curve. On a map, it becomes more jagged. Walking beside it, you find small bays, sharp rocks, curved beaches, narrow inlets, broken cliffs, tide pools, cracks in stone, tiny folds where water enters and retreats. Bend down even closer, and the edge becomes rougher still. Grains of sand, shells, wet pebbles, tiny channels carved by water, microscopic textures on rock. The coastline has not changed, yet your measurement of it has. This is the strange idea known as the coastline paradox. The length of a coastline depends on how closely you measure it. Use a long measuring stick, and you step over many details, drawing a simpler path from point to point. Use a shorter stick, and you are forced to follow more bends. Use an even smaller one, and more hidden edges appear. The result gets longer, not because the land is growing, but because your measurement is becoming sensitive to details you ignored before. This was studied seriously by scientists such as Louis Fry Richardson, and later made famous by Benoit Mandelbrot, who asked a question that sounds simple, but opens into something very deep. How long is the coast of Britain? The answer is not just one number. It depends on the scale of the ruler. That may feel uncomfortable, because we like measurements to be final. A table has a length, a road has a distance, a room has a width. But natural shapes do not always behave like clean objects from geometry class. They are rough, folded, broken, weathered, and layered. A coastline is not a perfect line. It is a living edge shaped by waves, tides, storms, erosion, sediment, wind, rock type, sea level, and time. It is not drawn once. It is constantly being revised. Waves eat into cliffs. Rivers carry sand outward. Storms tear beaches apart and rebuild them elsewhere. Tides move the boundary between land and water every day. Even the question, where exactly does the coastline begin, becomes harder than it first seems. Is it the high tide line, the low tide line, the cliff edge, the wet sand, the vegetation line, the legal boundary on a map? Each choice creates a slightly different coastline. This is not a failure of science. It is science becoming honest about the world's texture. The coastline paradox teaches that some things are not measured only by applying a ruler. They are measured by deciding what level of detail matters. If you are sailing near shore, small rocks and narrow channels may matter. If you are drawing a world map, they may disappear. If you are studying erosion, even a tiny crack in a cliff can become important. Measurement is not only about numbers. It is about purpose, and this is where the idea becomes more than a geography lesson. It reveals that reality can look different at different scales, and none of those views is simply fake. From space, a coast can be a smooth outline. From the ground, it is a maze. From the scale of sand grains, it becomes a universe of surfaces. The truth is not always one clean picture. Sometimes truth is layered, and the scale of your attention decides which layer appears. This is why coastlines are often connected to the idea of fractals, shapes that show roughness or repeated complexity at many levels of magnification. A real coastline is not a perfect mathematical fractal because physical limits exist. You cannot keep measuring smaller forever. Eventually you reach grains, molecules, atoms, and the shifting messiness of matter itself. The sea is moving, the land is changing. The line is never perfectly fixed. But over many practical scales, coastlines behave in a fractal-like way. The more detail you include, the longer and more intricate the boundary becomes. This helps explain why countries with jagged, fjord-filled, island-rich shores can have coastlines that seem enormous compared with their land area, while smoother coasts measure much shorter. Norway, for example, has a famously complex coastline because of its fjords and islands, so its measured length can vary greatly depending on the method used. This is why official coastline lengths from different sources may disagree. They are not always measuring the same thing in the same way. A number that looks simple may carry a hidden method inside it, and once you understand that, maps begin to feel less like final truth and more like carefully chosen summaries. A map is not the coastline itself. It is a decision about what to leave in and what to leave out. That does not make maps useless. It makes them human. It makes them tools. They simplify reality so we can navigate it, but every simplification has a cost. Something is always smoothed away. Some small curve is erased. Some tiny bay is ignored. Some roughness is made invisible so the larger shape can be understood. The coastline paradox reminds you that clarity often comes from omission. To see the whole, you sometimes have to lose the detail. To see the detail, you sometimes lose the whole. This tension lives everywhere. A human face from across a room is one expression. Up close it becomes pores, lines, shadows, tiny movements. A forest from a hill is a green mass. Inside it, each leaf, root, insect and fallen branch creates another world. A life from the outside may look like one simple story, but from within it is full of turns, interruptions, small wounds, private decisions, and invisible edges. The closer you measure anything real, the more complicated it becomes. That does not mean reality is unknowable. It means knowledge has scale. You must ask what you are trying to understand before you decide how closely to look. Too little detail can deceive you by making rough things seem smooth. Too much detail can overwhelm you until the larger pattern disappears. Wisdom is knowing when to zoom in and when to step back. The coastline does not give one easy answer because nature was not built to satisfy our desire for clean numbers. It was shaped by process, history, and constant change. The sea does not carve in straight lines. Wind does not polish every edge evenly. Time does not simplify everything for our convenience. It leaves complexity behind like handwriting. And perhaps that is the quiet beauty of this paradox. The world becomes longer, richer, and more intricate when you pay closer attention. What looked like a boundary becomes a story of pressure, movement, erosion, and patience. What looked like a line becomes a landscape. What looked like a number becomes a question about how deeply you are willing to look. So the next time you see a coast on a map, imagine all the hidden curves that have been smoothed away so your eyes can understand it. Imagine the cliffs, stones, shells, pools, and grains that the map cannot hold. And maybe remember that many things in life are like that coastline. Simple only from a distance, endless only when approached with care, and never fully captured by the first measurement you make. Simple rules can create worlds of complexity. A world can begin with a rule so small you could whisper it in one breath and still grow into something no one can fully predict by looking at the rule alone. That is the strange power of complexity. It does not always need a grand designer, a complicated blueprint, or an enormous starting plan. Sometimes it begins with a tiny instruction repeated again and again in the right environment. One cell follows a rule, then the next cell responds. Then thousands of tiny local decisions begin to touch, overlap, interfere, and build, until the result looks as if it must have been planned from above. But often there is no above. There is only the rule, the repetition, and the quiet accumulation of consequences. You can see this most clearly in simple computer worlds called cellular automata. Imagine a row or grid of tiny squares, each square able to be in one basic state, like on or off, light or dark. At each step, every square updates itself by looking only at its nearest neighbors and following a fixed rule. Nothing in the square understands the whole picture. Nothing has memory, intention, or imagination. And yet, when the rule repeats over many steps, patterns can appear that look shockingly rich. Stripes, nests, waves, triangles, broken textures, strange moving structures, and forms that seem almost organic. One of the most famous examples is Rule 30, studied by Stephen Wolfram. Its instruction is extremely simple, but when you let it run, it produces a pattern that looks irregular and deeply complex. So complex that parts of it have even been used for generating pseudo-random numbers in software. This is not because the rule is secretly intelligent. It is because simple local behavior can unfold into global surprise. That idea is one of the most important lessons in modern science. The whole is not always obvious from the parts. You can study one rule carefully, understand every word of it, and still be unable to easily picture the world it will create after thousands of repetitions. This is not the same as saying the result is magical. It is not magic. It is emergence. Emergence happens when many small interactions create a larger pattern with qualities that are not visible in any single piece. A single bird does not contain the shape of a flock. A single neuron does not contain a thought. A single water molecule does not contain the feeling of a wave. A single pixel does not contain an image. But when many pieces interact under simple rules, a new level appears. In the 1980s, computer scientist Craig Reynolds created a famous simulation of flocking behavior called boids. The artificial birds followed only a few basic rules. Avoid crowding nearby birds, steer toward the average direction of neighbors, and stay close enough to the group. From those simple instructions, the simulated flock began to move in a way that felt natural, fluid, and alive. There was no leader controlling the entire group, no master bird drawing the pattern in the sky. The flock emerged from local responses. Each bird only reacted to nearby birds, yet the whole group curved, split, and rejoined as if guided by a shared mind. This teaches something profound about nature. Coordination does not always require central control. Sometimes order rises from many small freedoms constrained by simple rules. The same principle helps explain why schools of fish can turn together so quickly, why crowds can form lanes when people walk in opposite directions, why crystals grow into repeating structures, and why patterns in living systems can appear without anyone drawing them first. A snow crystal, for example, does not receive an artistic plan before forming. Its shape grows from water molecules attaching under conditions of temperature and humidity, guided by the geometry of ice and the environment around it. The final structure can look delicate, almost impossible, but it emerges step by step from physical rules. In biology, the story becomes even more intimate. The body does not build itself from a complete visible map, where every cell is told its final location, like a worker reading an architectural plan. Development is more dynamic than that. Cells respond to chemical signals, to neighboring cells, to timing, to gradients, to genes switching on and off. A tiny embryo becomes a body through layers of simple but coordinated instructions, feedback, and local communication. Each cell does not know the whole person, yet the whole person grows. This is one of the most humbling truths in science. Life is not assembled like a machine from the outside. It organizes itself from within, through rules that are simple in pieces but astonishing in combination. And once you understand this, you start seeing complexity differently. You stop assuming that a complicated result must have a complicated cause. Sometimes a city's rhythm grows from countless small routines. People waking, buying bread, opening shops, catching buses, answering messages, avoiding crowds, following habits. No single person controls the city's pulse, yet the city has one. Sometimes language changes because millions of speakers repeat tiny preferences, shorten words, borrow sounds, and pass expressions along. No one designs the whole evolution of speech, yet languages drift, split, and reshape over centuries. Sometimes culture itself behaves like an emergent system, where trends, beliefs, fears, jokes, and ideas spread through simple acts of imitation and response. Each person may feel individual, and they are, but the larger pattern is built from interactions too numerous for one mind to hold. This is why simple rules can be both beautiful and dangerous. A helpful rule repeated across many people can create cooperation, trust, and shared stability. A harmful rule repeated without thought can create systems that feel bigger than anyone intended. A small incentive can reshape behavior across an entire organization. A small design choice in an app can influence how millions of people pay attention. A small habit in your own life can grow into a personality trait, not because it was dramatic at the beginning, but because repetition gave it structure. Complexity is patient. It does not need to announce itself. It grows quietly through small actions that reinforce one another. That is why this idea should make you both curious and careful. If simple rules can create worlds, then the rules you live by matter. The small defaults matter. The tiny repeated choices matter. What you reward, what you ignore, what you practice, what you return to when no one is watching. These are not isolated moments. They are instructions being run again and again inside the system of your life. Over time, they can create patterns that feel larger than you, but they can also be changed at the level where they began. You do not always need to redesign the entire world at once. Sometimes you change the rule. Sometimes you adjust the local interaction. Sometimes you alter what happens repeatedly, and the larger pattern slowly becomes different. That is the quiet hope inside complexity. It tells you that the world is not only shaped by massive forces, but also by tiny principles repeated with enough time. It tells you that intelligence is not always found in one controlling center, but in relationships, feedback, adaptation, and accumulation. It tells you that the ordinary can become astonishing when it is allowed to iterate. So when you hear that simple rules can create worlds of complexity, do not imagine simplicity as weakness. Imagine it as a seed, a small instruction placed inside time, a quiet beginning that does not yet reveal what it can become. Because somewhere between the first step and the thousandth, between the single cell and the living body, between the one rule and the unfolding pattern, something new appears, not imposed from outside, but awakened from within. Nature repeats, similar shapes at different scales. A fern leaf does something quietly impossible looking. It holds a smaller version of itself inside itself, as if nature has learned to echo its own handwriting at different sizes. Look closely at one fern frond, and you see a long, graceful shape made of smaller leaflets. Look closer at those leaflets, and many of them resemble the larger shape they belong to. The pattern is not perfectly copied like a stamp, and that matters, because nature rarely repeats with machine precision. It repeats with variation, with softness, with living imperfection. But the resemblance is strong enough to make you pause. The small seems to remember the large. The part carries the rhythm of the whole. This kind of repetition across scale is one of the most beautiful clues that nature is not simply messy, even when it looks wild. It often builds by reusing forms, repeating strategies, and letting one pattern appear again at another level. Scientists call this kind of pattern self-similarity, when parts of a shape resemble the whole, and it appears in many natural forms, from plants and branching systems to mountain ridges. Ice crystals, blood vessels, lightning paths, and the delicate shapes of certain vegetables like Romanesco broccoli. But the deeper lesson is not that nature is copying itself for decoration. The deeper lesson is that repeating similar shapes at different scales can be useful. It can help living things collect light, move fluids, exchange gases, spread nutrients, drain water, resist stress, and fill space efficiently. A plant does not have to invent a completely new design for every branch, every vein, every leaf edge. It can repeat a successful pattern with adjustments, building a larger body from smaller echoes. This is why a tree can look like a tree at many scales. The trunk divides into branches, branches divide into smaller branches, and those smaller branches divide again into twigs. The pattern is not random scribbling. It helps distribute water and nutrients while also spreading leaves into sunlight. The shape is both beautiful and practical. It is form-serving function. Your own body carries similar logic in hidden places. Blood vessels branch from large arteries into smaller vessels and then into tiny capillaries, reaching tissues that need oxygen and nutrients. The lungs branch too, dividing airways into smaller and smaller passages so that air can reach a vast inner surface where oxygen enters the blood. These patterns do not exist because nature loves symmetry in a poetic sense. They exist because branching solves a problem: how to connect a large region through many smaller pathways without wasting too much material or energy. A single thick tube could not reach every cell efficiently. A branching network can, and this is where repeating shapes become a kind of intelligence without thought. No branch needs to understand the whole tree. No blood vessel needs to understand the whole body. The pattern works because the same basic strategy can be applied again and again at different sizes. You see another version of this in river systems. A small stream joins a larger stream, then a larger river, then a main channel moving toward the sea. From above, a river basin can look strangely similar to a branching plant or a network of veins. The materials are different: water, soil, stone, gravity, time. But the problem is related. Collect flow from many small places and move it through connected paths. Nature often repeats shapes because different systems face similar challenges. How do you spread? How do you gather? How do you transport? How do you survive pressure? How do you fill space without filling it wastefully? Similar problems can lead to similar forms even when the objects themselves are unrelated. This is why patterns in nature can feel familiar before you know why. A lightning bolt branching through the sky can resemble the roots of a plant, not because lightning is alive, but because both are shaped by paths of least resistance through complex environments. Lightning searches for an electrical route through air. Roots explore soil for water and nutrients. The forces are different, but the branching logic carries an echo. Mountain ridges too can show repeating roughness at different scales. A large ridge has smaller ridges. Those smaller ridges have cracks and textures. And from far away, the landscape can look like a pattern that keeps unfolding as you approach. Again, it is not perfect repetition. Natural self-similarity is often approximate. That distinction is important. Real nature is not a clean mathematical drawing. It is shaped by wind, growth, friction, damage, history, temperature, chemical gradients, gravity, and chance. A fern may repeat its form, but every leaflet is not identical. A snow crystal may show repeating symmetry, but each arm grows through tiny changes in humidity and temperature. A cloud may look similar at several scales, but it is constantly moving and dissolving. The repetition is alive, not mechanical. It is a family resemblance, not a photocopy. This makes nature's patterns more interesting, not less. They show that order does not have to be rigid to be real. A pattern can bend, break, adjust, and still remain recognizable. And perhaps that is why these shapes feel so calming to look at. Your mind senses structure without feeling trapped by it. You see repetition but not boredom. You see variation but not total chaos. Natural patterns often sit in that quiet middle space between sameness and disorder, where the world feels understandable yet still mysterious. This is also why these forms inspire art, architecture, computer graphics, and design. When artists create realistic landscapes or digital plants, they often use repeating structures at different scales because the eye recognizes that this is how the real world behaves. A mountain that is smooth at every scale looks fake. A tree with branches placed without any repeating logic looks wrong. A cloud drawn as a simple cotton ball does not feel like a cloud. Real natural beauty often comes from layered detail. Large structure, medium structure, tiny structure, all speaking the same visual language in different voices. But there is also a philosophical question hiding here. Why should the world reuse shapes? Why should the same kinds of patterns appear in leaves, rivers, lungs, lightning, roots, and landscapes? The answer is not that everything is secretly the same thing. The answer is more subtle. Nature is built under constraints. Energy must move. Materials must be saved. Surfaces must grow. Fluids must travel. Living systems must feed themselves. Forces must find pathways. When different systems face similar pressures, similar forms can emerge. Nature repeats not because it lacks imagination, but because some solutions are powerful enough to appear again and again. This changes how you look at the world. A leaf is no longer just a leaf. It is a visible answer to the problem of sunlight. A lung is not just an organ, it is a branching architecture for meeting air. A river is not just water moving downhill, it is a network writing gravity into land. And you, standing among these patterns, are not outside them. Your body is made of repeating structures too. Cells forming tissues, tissues forming organs, nerves branching into sensation, vessels carrying life through narrowing paths. You are not simply looking at nature's self-similarity, you are part of it. The same world that builds trees with branches builds you with networks. The same logic that lets a fern unfold lets your lungs breathe. So the next time you see a shape in nature that seems to echo itself, a leaf within a leaf, a branch within a branch, a river within a river of smaller streams, do not dismiss it as decoration. See it as evidence of a deeper economy, a way the world creates richness without needing endless new instructions, a way life and matter turn repetition into beauty and beauty into function. Nature repeats similar shapes at different scales, because the universe often builds with memory. Not the memory of a mind, but the memory of useful forms, carried through matter, growth, pressure, and time. And once you notice that quiet echo, the world begins to feel less like a collection of separate objects, and more like a single language spoken in different sizes. A shape can have infinite perimeter, but finite area. A shape can be trapped inside a limited space and still have an edge that never truly ends. That sounds impossible at first because your everyday experience tells you that if something fits on a page, or inside a frame, or within the outline of a small drawing, then its boundary should also be limited in a simple way. You imagine a circle, a square, a triangle, and the rule feels obvious. The area is the space inside, and the perimeter is the distance around the outside. Make the shape bigger, and both can grow. Make it smaller, and both can shrink. But mathematics has a way of finding hidden doors inside ideas that feel settled. And one of those doors opens into a strange object often called the Koch snowflake. It begins very innocently, with a simple triangle. Nothing about the first step feels strange. 3 sides, 3 corners, a clean little island of space. Then each side is changed. A small triangular bump is added to the middle of every side, turning the shape into something more like a rough star. Then the same operation is done again to every new little side. Then again, and again. Each step adds more detail to the boundary, more corners, more turns, more tiny edges. The shape becomes increasingly delicate, like a snowflake being carved by an infinitely patient hand. But here is the part that disturbs common sense. As this process continues forever, the perimeter grows without limit, while the area inside approaches a fixed amount. In plain language, the edge becomes infinite, but the space it surrounds does not. You could cover the inside with a finite amount of paint, at least in the mathematical ideal, but you could never finish tracing the border if every tiny bend had to be followed completely. This is not a trick of language. It is one of those precise mathematical results that reveals how different inside and around can become when a shape is allowed to develop endless detail. The reason is gentle but surprising. Each time the boundary is modified, it becomes longer. The total edge is multiplied by a little more than before, step after step, so it keeps increasing without ever settling. But the new area added at each stage becomes smaller and smaller. The first added bumps contribute a visible amount of space. The next ones add less. The ones after that add even less. Eventually, the additions become so tiny that, when all of them are gathered together, they approach a final limit instead of growing forever. It is like adding smaller and smaller sips of water into a cup that never overflows, while the thread wrapped around the cup somehow keeps getting longer without end. This separation between boundary and area is the heart of the wonder. It shows that a shape can have two kinds of size at once, one that remains controlled and one that escapes completely. And this forces you to question the simple pictures you carry in your mind. A boundary is not always a smooth fence around a field. Sometimes the fence can fold, wrinkle, and branch into detail so fine that its total length becomes endless, even though the field it encloses remains modest. The Koch snowflake is an ideal mathematical object, not something you can build perfectly from metal or draw fully with ink, because the physical world eventually reaches limits. Atoms, material thickness, imperfect tools, time and motion. A real pen line has width, a real edge is made of matter. You cannot keep adding smaller and smaller corners forever in a physical object. But mathematics lets the process continue in thought, without friction, without blunting, without running out of patience. That is what makes it powerful. It does not claim you will find a perfect infinite edge snowflake lying on a table. It reveals what happens when a rule is carried to its pure conclusion. And sometimes those pure conclusions teach us how strange the relationship between measurement and form can be. This kind of shape also helps explain why smooth geometry, the kind learned early in school, is only one language for describing the world. Circles, squares, and straight lines are beautiful and useful, but many real boundaries are rougher, richer, and harder to summarize. A cracked surface, a torn piece of paper, a cluster of crystals, a jagged line of frost on glass. These are not always well described by the clean shapes of classical geometry. They require a way of thinking that respects detail at many levels. The infinite perimeter and finite area idea shows that roughness is not just decoration. It can change the very meaning of length. It also separates two forms of infinity that your intuition may try to blend together. Infinite boundary does not mean infinite space. Endless edge does not mean endless inside. Something can be limited in one sense and unlimited in another. That is a deeply useful thought, because many things in life are like that. A small memory can have an edge that never seems to finish, because every time you examine it, another detail appears. A short conversation can contain more emotional turns than its length suggests. A simple decision can be surrounded by endless consequences, while the decision itself occupies only a moment. Of course, mathematics is not saying your feelings are snowflakes, or that life follows this exact construction, but it gives you a clean image for a real experience. The inside of something and the boundary of something are not always proportional. The space a thing occupies may be small, while the complexity of approaching it may be enormous. This is also why the shape feels almost philosophical. It asks what it means to know a thing. If you say you understand the shape because you know the area it covers, you miss the endless complication of its edge. If you focus only on the perimeter, you may forget that the whole object still fits within a finite region. Knowledge often works this way. One view gives you containment, another gives you complexity. Neither alone is complete. The snowflake teaches you that reality can be bounded without being simple. It can be finite without being easy. It can live inside a frame and still contain an inexhaustible border. And perhaps this is why the idea stays in the mind after the explanation is over. It does not merely give you a strange fact. It changes the way you look at edges, the edge of a thought, the edge of a problem, the edge of what you think you understand. From far away, many things look finished. Their outline seems clear, their size seems knowable. But when you move closer, when you follow every turn with care, the boundary begins to lengthen. More details appear, more questions open, more hidden corners ask to be traced. So the next time you see a simple shape, or a simple answer, or a simple story, remember the snowflake that can be painted, but never fully fenced. Remember that the inside may be finite while the edge stretches beyond all completion. And maybe let that become a quiet lesson. Some things are not infinite because they are huge, but because the closer you look, the more boundary they reveal. The same patterns appear in cities, language, and wealth. A city skyline, a page of language, and a list of fortunes should have nothing in common. Yet if you arrange them carefully, they begin to whisper the same hidden pattern. One belongs to concrete, roads, electricity, apartments, bridges, and human movement. One belongs to breath, memory, grammar, and the tiny choices of speech. One belongs to money, ownership, opportunity, inheritance, risk, and power. They feel like different worlds. But when researchers count them at scale, a strange resemblance appears. A few cities become enormous while most remain small. A few words appear constantly while most words are rare. A few people or institutions hold enormous wealth while many hold very little. This does not mean cities, language, and wealth are the same thing. And it does not mean one simple rule explains all inequality, all speech, or all urban growth. Reality is more complicated than that, but it does show something deeply important. When many human choices pile up over time, they often do not spread evenly. They form steep patterns. The largest examples become much larger than ordinary intuition expects, while the smallest and rarest examples remain numerous. In language, this is easiest to feel. Open almost any long book, article, or transcript and count the words. You will find that a tiny group of words does most of the work. Words like the, of, and, to, in, and you appear again and again, quietly carrying the structure of speech. Then come less common words, then rarer words, then words so rare they may appear only once. The vocabulary of a language is vast, but daily communication depends heavily on a small core. This pattern is often connected with Zipf's law, a famous observation that the most common word tends to appear far more often than the second more than the third, and so on in a smooth falling pattern. It is not perfect in every text, and language is not a machine, but the pattern appears often enough to feel like a hidden grammar beneath grammar. Why does this happen? Partly because language must balance effort and meaning. Common words are useful because they connect everything. They are short, flexible, and constantly needed. Rare words survive because humans need precision, beauty, identity, and difference. A language made only of common words would be efficient but dull. A language made only of rare words would be rich but exhausting. So language becomes layered. A few words as roads everyone travels, many words as narrow paths used only when needed. Now move from language to cities. A country may have one or two giant cities, several large ones, many medium ones, and countless small towns. The biggest city is often not just slightly bigger than the others. It may become a magnet for jobs, universities, culture, hospitals, airports, media, political attention, and ambition. People move there because opportunities are there, and opportunities grow there because people move there. This creates a feedback loop. A city that is already large can attract more connections, and more connections can make it larger still. But this growth is not only about size. Cities also become more productive and more intense in certain ways as they grow. Urban researchers have found that many features of cities scale with population. Roads, infrastructure, patents, income, crime, energy use, disease spread, and social interaction can change in systematic ways as cities get bigger. Again, this does not mean every city follows one simple destiny. History, geography, policy, migration, climate, industry, war, and culture all matter. But cities are not random piles of buildings. They are networks of human interaction, and networks often reward connection. The more people live close enough to meet, trade, learn, argue, hire, imitate, compete, and cooperate, the more the city becomes a living engine. The city grows not only outward, but inward, through relationships. A small town may have beauty, calm, and community, but a giant city has density, and density changes the mathematics of possibility. More people means more possible encounters. More encounters means more ideas, more businesses, more pressure, more speed, more stress, more invention. The city becomes a physical version of a sentence where some words become unavoidable because everything passes through them. Then consider wealth, the most emotionally charged of the three. Wealth distribution often shows a similar steepness. A minority holds a large share, while many people hold much less. This is not because money has a mind, and it is not because every rich person becomes rich for the same reason, or every poor person remains poor for the same reason. But wealth can accumulate through mechanisms that reinforce themselves. Money can earn returns, property can rise in value, access to education, credit, networks, safety, time, and opportunity can compound. A person who starts with more resources may be able to take better risks, survive failure more easily, invest earlier, borrow more cheaply, move to better locations, and connect with more influential circles. Meanwhile, a person with fewer resources may spend most of their energy simply resisting collapse. This is why wealth can behave less like water poured evenly across a table and more like snow rolling downhill, gathering mass where conditions allow. Small early differences can become large later differences when the system rewards what is already ahead. In science and economics, people sometimes call this cumulative advantage, and in everyday language, it often appears as success breeds success. The phrase can sound cold, but the reality is human. It affects neighborhoods, families, schools, businesses, and futures. It shows why patterns in wealth are not only personal stories, but structural stories. They reveal how systems amplify some beginnings and bury others. And here is the deep connection between cities, language, and wealth. All three are shaped by repeated choices inside networks. A word becomes common because people keep using it, and people keep using it because it is already understood. A city becomes powerful because people keep gathering there, and people keep gathering there because it is already powerful. Wealth grows because resources can create more resources, and more resources can create more chances to grow. In each case, the present is shaped by the past, and the past keeps echoing into the future. Popularity attracts more popularity. Connection attracts more connection. Advantage attracts more advantage. But this does not mean the pattern is morally good, or that it should simply be accepted. Mathematics can describe a pattern without approving of it. A distribution can be natural in the sense that it commonly emerges, while still being harmful, unfair, or worth changing. This distinction matters. When you see that similar patterns appear in cities, language, and wealth, you should not conclude that inequality is inevitable in every form, or that human systems cannot be improved. You should conclude that large systems have tendencies, and if those tendencies are ignored, they can quietly become stronger. A city can become too dominant if all roads, jobs, and institutions flow toward it. A language can lose diversity if only the most common words and voices are amplified. Wealth can concentrate if systems allow existing advantage to multiply without balance. Understanding the pattern gives you a tool, not an excuse. It lets you ask better questions. Who benefits from the feedback loop? Who is left outside it? Which connections are being rewarded? Which voices are becoming invisible because they are not already large? Which small places, small words, or small lives contain value that the pattern fails to protect? This is where the science becomes reflective. The same kind of shape can appear in a city map, a dictionary, and a bank ledger because humans are not isolated dots. We live through attention, imitation, exchange, memory, and accumulation. We repeat what is useful. We move toward what is connected. We invest where growth seems likely. We speak in words others recognize. We gather in places where others have gathered. Slowly, the world becomes uneven, not always because someone planned the unevenness, but because countless small acts reinforce certain paths. And once a path becomes wide, it becomes easier for more footsteps to follow it. That is why the largest things in human systems often feel almost gravitational. A famous city pulls migrants. A common word pulls usage. A large fortune pulls opportunity. The pattern is not destiny, but it is momentum. And momentum must be understood before it can be redirected. So when you hear that the same patterns appear in cities, language, and wealth, do not imagine a shallow coincidence. Imagine a deeper signature of human systems. The way attention gathers, the way connection multiplies, the way advantage compounds, the way small differences can become visible architecture. A skyline, a sentence, and a fortune may look unrelated, but beneath them all is the same quiet warning and the same quiet wonder. What grows large often grows easier to see, easier to use, easier to choose again, while what remains small may still be numerous, meaningful, and alive. And perhaps the most important question is not why the pattern exists, but what we decide to do once we can finally see it. Benford's law detects strange number distributions. The strangest lie in a spreadsheet may not hide in the biggest number, but in the quiet pattern of all the numbers together. One entry can look harmless. One receipt, one population figure, one invoice, one expense, one measurement, one reported value. By itself, it may not reveal much at all, but when many numbers are placed side by side, they begin to develop a kind of fingerprint. Not a fingerprint of a person exactly, but of a process. Real-world numbers often carry the trace of how they were produced. Growth, counting, measuring, pricing, accumulating, expanding, shrinking, recording. And when that trace is disturbed, when the numbers look a little too smooth, a little too balanced, a little too human in the wrong way, Benford's law can sometimes raise its hand and whisper, "Look again." This is why the idea is so fascinating. It is not simply a curiosity about which digit appears first. It is a tool for detecting when a collection of numbers does not behave the way certain natural datasets often behave. In accounting, auditing, tax analysis, scientific data checks, insurance claims, and large financial records, Benford's law can help investigators notice unusual distributions that might deserve closer attention. But the key word is help. It does not convict. It does not prove deception by itself. It does not replace context, evidence, or human judgment. It is more like listening to the rhythm of a room and noticing one instrument is slightly out of tune. Something may be wrong, or there may be a perfectly innocent reason. The power of Benford's law is not that it gives a dramatic answer, but that it helps ask a sharper question. If a company reports thousands of expenses, and the leading digits appear in a pattern that is very different from what Benford's law would suggest for that kind of data, an auditor may decide to examine the records more carefully. Maybe someone fabricated numbers. Maybe invoices were split or rounded. Maybe a reporting system created artificial limits. Maybe the dataset simply is not the type that should follow Benford's law in the first place. That last point matters deeply, because using this law without understanding it can become its own kind of mistake. Benford's law works best with datasets that span several orders of size and are not assigned by human design. Street addresses, passport numbers, product codes, and fixed price lists may not follow it because they are structured artificially. Human ages in a classroom will not follow it well because they sit inside a narrow range. Numbers forced between strict minimum and maximum values may not follow it either, but naturally generated quantities that vary widely, like sales amounts, utility bills, river drainage sizes, city populations, company revenues, or scientific measurements, often come closer. This is because they are not merely chosen. They are produced by processes that stretch across scale, and scale leaves marks. A person inventing numbers, however, often imagines randomness incorrectly. The human mind tends to distribute digits too evenly, as if a believable dataset should give every leading digit a fair share. But many real datasets are not fair in that simple way. They lean, they have a shape, they are uneven for a reason. This is where Benford's law becomes quietly forensic. It uses the fact that humans are often bad at imitating natural irregularity. When someone makes up figures, they may avoid too many numbers starting with the same digit because that feels suspicious to them. They may overuse middle digits. They may round too often. They may produce numbers that look random to the eye, but lack the deeper texture of naturally generated data. In this sense, Benford's law does not catch the lie directly. It catches the difference between human imitation and organic numerical behavior. It asks whether the numbers smell like the world or like someone's imagination. This idea has been used in fraud detection, especially in accounting, where researcher Mark Negrini helped popularize practical applications of Benford analysis for financial data. Investigators may look not only at the first digit, but also at second digits, first two digits, repeated patterns, unusual spikes, and deviations from expected distributions. A strange pattern may guide them toward transactions worth examining. For example, if expense claims cluster just below an approval limit, that may suggest people are shaping the numbers to avoid review. If certain digit combinations appear far more often than expected, that may point to copying, rounding, or artificial construction. But again, the law is a signal, not a sentence. A dataset can fail Benford tests because it has been filtered, capped, rounded, seasonally affected, legally constrained, or collected from a narrow business process. A small dataset can look strange simply because there are not enough numbers for the pattern to settle. A clean Benford match does not prove honesty either, because a sophisticated fraudster could design fake numbers to resemble it. The truth is more subtle, and that subtlety is what makes the topic worth understanding. Benford's law is not a magical fraud detector. It is a way of noticing when numbers deserve attention. It turns suspicion from a feeling into a question that can be tested, and that is a powerful shift. Instead of looking at numbers one by one and asking, "Does this entry feel wrong?" you look at the entire population of numbers and ask, "Does this collection behave like this kind of collection should?" That is a different way of seeing. It is no longer about the single dramatic clue. It is about the shape of the whole. Science works this way often. A single measurement may not mean much. A pattern of measurements may mean everything. In public health, one unusual case may be random, but a cluster may reveal an outbreak. In finance, one odd transaction may be innocent, but many odd transactions may reveal a scheme. In research, one surprising result may be noise, but repeated deviations may suggest a problem in the method. Benford's law belongs to that family of thinking. It reminds us that truth often hides not in the loudest detail, but in the distribution. And that word, distribution, is quietly important. It means the way values spread out, the way they gather, the way they avoid some places and favor others. Most people look at numbers for their content. How much, how many, how high, how low. Benford's law asks you to look at numbers for their behavior. Are they too neat, too flat, too clustered, too convenient? Too rounded, too artificial? The emotional lesson is almost uncomfortable. Deception may not always look like a monster. Sometimes it looks like tidiness. Sometimes false numbers look suspicious because they are too balanced, too evenly spread, too obedient to what a human thinks randomness should be. Real data can be messy in a very specific way. It can carry scars of growth, scale, friction, timing, and measurement. Fake data may carry the smoother fingerprints of intention, and once you realize that, numbers become less cold. They become almost alive with history. A row of invoices is no longer just accounting. It is a record of decisions, purchases, approvals, habits, pressures, and maybe concealment. A table of scientific readings is not only data. It is the shadow of instruments, methods, environments, and human care. A dataset is a landscape, and Benford's law is one way of looking for strange footprints in the soil. But it also teaches caution against becoming too eager to accuse. A pattern can be strange without being dishonest. A distribution can be unusual because the system itself is unusual. Good analysis asks why before it declares what. That is the discipline hidden inside the wonder. Benford's law gives you a lens, but you must still decide where to point it and how carefully to interpret what you see. In a world overflowing with numbers, revenue, rankings, statistics, views, prices, polls, claims, records, this matters more than ever. We are surrounded by figures that ask to be trusted. Some are real, some are distorted. Some are selected to persuade. Some are shaped by systems we do not see. Benford's law does not solve that problem, but it gives the mind a quiet defense. It says, do not only read the number, study the crowd it belongs to. Do not only ask whether one value is possible, ask whether the whole pattern feels naturally produced. Do not be hypnotized by precision, because a number can have decimal places and still be false. So when you hear that Benford's law detects strange number distributions, imagine a lamp held over a field of figures. It does not reveal everything. It does not replace investigation, but it can show where the ground looks disturbed. It can turn a spreadsheet into a crime scene, a scientific table into a self-check, a financial report into a pattern waiting to be tested. And maybe the deeper lesson is this: reality has texture, and lies often struggle to imitate texture perfectly. The world does not always arrange its numbers the way the human mind expects. That is exactly why the numbers can sometimes protect the truth. Not by speaking loudly, but by leaning in a direction that careful eyes know how to notice. Zipf's law appears in language and population. A single word repeated millions of times and a giant city glowing at night may seem unrelated, but both can reveal the same quiet law of rank. Imagine lining up every word in a long book from most common to rarest, then doing the same with cities in a country from largest to smallest. You might expect the list to fall in a messy, unpredictable way, because language comes from thought, and cities come from history, geography, jobs, roads, politics, and human movement. But again and again, researchers have noticed a strange pattern. The first item is often much larger or more frequent than the second. The second is often larger than the third larger than the fourth, and the decline follows a surprisingly regular shape. This is commonly known as Zipf's law, named after linguist George Kingsley Zipf, who studied how often words appear in language and connected the pattern to what he called the principle of least effort. In simple terms, humans tend to communicate in ways that balance two needs. The speaker wants to use familiar, easy words, while the listener needs enough variety to understand meaning. If every idea had its own completely unique word, language would be impossible to learn. If only a few words existed, communication would be too vague. So language settles into a living compromise. A small number of words are used constantly because they are useful everywhere, while many other words wait in the background for more precise moments. The word "the" may appear thousands of times in an English book, while a word like microscope may appear only a few times, and a rare technical word may appear once or not at all. This does not mean language is mechanical or lifeless. It means that beneath the creativity of speech, there is a hidden economy. Words compete for attention, usefulness, memory, and ease. The most useful words become roads everyone travels. The rare words become quiet side streets, not less valuable, but more specialized. And this is why Zipf's law can feel so strange. It shows that even something as human, emotional, and creative as language can develop a mathematical-looking rhythm without anyone planning it. No committee decides that the most common word should appear so often, or that the 10th most common word should appear roughly a certain amount. The pattern emerges from millions of choices made by speakers and writers trying to be understood. Now shift from words to populations. In many countries, if you rank cities by population, the largest city may be about twice the size of the second, about 3 times the size of the third, and so on. Though real countries often deviate because history is never perfectly smooth. This is sometimes called the rank size rule, and it is related to the same family of patterns as Zipf's law. It does not work perfectly everywhere. Some countries have one dominant capital that towers over all other cities. Some have several strong regional centers. Some are shaped by mountains, coastlines, borders, colonial history, political decisions, industry, war, or planned development. But the fact that any regular pattern appears at all is remarkable. Cities are not words, yet they can arrange themselves by rank in a similar falling order. Why? Because cities, like words, are shaped by use and connection. A large city offers more jobs, schools, hospitals, markets, transportation links, entertainment, and social possibilities. Those advantages attract people. More people then create more services, more businesses, more demand, and more reasons for others to come. But smaller cities still matter because not every person, industry, or culture can concentrate in one place. A nation needs many centers of life, just as a language needs many levels of vocabulary. The largest city may serve as a major hub, but smaller cities carry regional identity, local trade, family networks, and forms of life that a megacity cannot replace. In this way, a country's population map can resemble a language, a few very common centers, many moderately common ones, and a long tail of smaller places that still hold meaning. The lesson is not that cities and words are the same, but that ranking can reveal hidden structure across very different systems. When things are used, chosen, visited, repeated, spoken, or inhabited by many people, they often form hierarchies. The top ranks become highly visible, the lower ranks become numerous, and somewhere between them is a smooth descent that tells you the system is neither fully equal nor completely random. This is important because Zipf's law changes how you think about popularity. Popularity is not always just quality. A word can be common because it is useful, short, old, flexible, and deeply woven into grammar. A city can be large because of location, history, infrastructure, political power, economic opportunity, and timing. Once something reaches a high rank, it becomes easier for it to remain important because many other things are organized around it. But Zipf's law also reminds us that the rare and the small do not disappear. In language, rare words give precision, beauty, and identity. Without them, thought would flatten. In population, smaller towns and cities preserve local knowledge, slower rhythms, cultural memory, and different ways of belonging. The long tail is not waste. It is diversity. A healthy language needs both the common word and the rare word. A healthy country often needs both the great city and the small place. The danger comes when we mistake rank for worth. The most frequent word is not always the most beautiful. The largest city is not always the most livable. The highest position in a list tells us something about structure, but it does not tell us everything about value. That is where the pattern becomes philosophical. We live in a world obsessed with rankings. Most viewed, most spoken, most populated, most searched, most followed, most repeated. Zipf's law shows that ranking is not just a cultural habit. It often reflects how large systems organize themselves. But it also asks us to look beyond the top of the list. The first place is loud, but the full shape of the list matters. The rare words, the quiet towns, the small communities, the almost forgotten names, they are part of the system's richness. If everything became concentrated only at the top, the world would become efficient but fragile, recognizable but thin. Complexity needs a long tail. It needs common paths and hidden paths. It needs central hubs and distant edges. So when you hear that Zipf's law appears in language and population, do not imagine a cold formula controlling human life. Imagine a pattern that rises from countless small acts. Speaking, moving, choosing, settling, remembering, repeating. Imagine a book where a few words hold the sentences together while thousands of others wait like stars in the background. Imagine a country where a giant city pulls attention like a sun, while smaller places keep their own quiet gravity. And maybe the deepest lesson is this: human systems often create order without anyone seeing the whole. We speak, travel, gather, and choose from close range, but from far away, our choices draw curves in the dark. Zipf's law is one of those curves, a reminder that beneath the noise of language and the lights of cities, there may be a hidden rhythm of use, effort, memory, and scale, shaping the way human life arranges itself. Fractals describe trees, lungs, rivers, and clouds. A cloud may look soft enough to touch, but mathematically, it is one of nature's quiet warnings that the world is not built from clean circles and straight lines. From a distance, a cloud seems like a simple white shape floating above you, a loose island of vapor drifting through the sky. But as you look closer, its edge begins to break apart into smaller curves, wisps, bulges, gaps, and dissolving threads. Look closer still, and those smaller forms break into even finer textures, shaped by air currents, temperature, moisture, sunlight, and motion. A tree does something similar in wood and leaf. A river does it in land and water. Your lungs do it in breath. None of these things are perfect mathematical fractals, because real nature has limits, materials, damage, growth, and time, but they are fractal-like in a deeply useful way. Their structure repeats or roughens across many levels, allowing them to fill space, move energy, transport fluids, exchange gases, and create enormous contact with the world without becoming solid blocks. This is why fractals matter. They are not just beautiful patterns for posters or computer screens. They are a language for describing the kinds of shapes classical geometry struggles to hold. A circle is easy, a cube is easy, a smooth cone is easy. But how do you describe the rough edge of a cloud, the branching of a river basin, the fine division of lungs, or the layered structure of a forest canopy? You need a different kind of thinking, one that accepts that real forms are often irregular but not meaningless. Fractals help us study roughness with discipline. They let scientists ask how detail changes as you zoom in or out, how much space a pattern fills, how branching networks distribute flow, and how complex surfaces interact with their environment. Take a tree. Its branching is not only a visual pattern, it is a survival strategy. The trunk lifts the structure, large branches spread outward, smaller branches carry leaves into light, and the whole form allows the tree to expose a vast leaf surface to the sun, while keeping the amount of wood within practical limits. If all the leaves were attached to one flatboard, the design would fail. If the branches did not divide, many leaves would be shaded or unsupported. The fractal-like branching gives the tree reach. It turns a rooted organism into a living collector of light. Now think of the lungs. Inside your chest, the airways do not end after one or two divisions. They branch again and again, becoming smaller passages that lead to tiny air sacs where oxygen can pass into the blood. This architecture creates a huge internal surface area inside a limited body. You do not need lungs the size of a room because branching folds the contact surface inward. The same idea appears in blood vessels, roots, and many transport networks. Divide the pathway, reach many places, reduce distance, and increase exchange. Nature often builds not by making one giant opening, but by creating many smaller ones. Fractal-like design is a way of turning limitation into access. Rivers offer another version. Rain does not fall neatly into one channel. It lands across hills, slopes, forests, farms, rocks, and soil, then gathers into tiny streams, then larger streams, then rivers. The pattern of a drainage basin records how water has negotiated gravity and landscape over time. It shows the history of slopes, erosion, rainfall, rock hardness, and flow. A river network is not only a path for water, it is the memory of land being shaped. Its fractal-like branching helps collect water from a wide area and move it toward lower ground. And clouds, though they seem almost weightless, reveal yet another face of the same idea. Their rough edges are shaped by turbulent air, where swirling motions break into smaller motions, and those smaller motions break again. This does not mean every part is a perfect copy of every other part, but it does mean the cloud carries structure across scales. Its softness is not simplicity, it is motion made visible. This is one reason fractals became important in computer graphics. Early digital landscapes often looked fake because they were too smooth. Real mountains are not polished pyramids. Real clouds are not cotton circles. Real trees are not simple sticks with green spheres attached. To create believable nature on a screen, artists and programmers needed controlled roughness, layered detail, branching, and variation. Fractal methods help generate mountains, coastlines, plants, clouds, flames, textures, and landscapes that felt more natural because they had complexity at many scales. Your eye knows the difference, even before your mind explains it. A fake mountain looks smooth where it should be scarred. A fake cloud looks solid where it should dissolve. A fake tree looks assembled where it should grow. Fractals help digital nature breathe by giving it the kind of irregular order your brain expects from the real world. But fractals are not only useful for images. In medicine, researchers can study the branching patterns of blood vessels, airways, tumors, and tissues to detect changes that may signal disease. In ecology, fractal ideas can help describe habitats, plant structures, animal movement paths, and the edges where one environment meets another. In geology, They help describe cracks, fault lines, porous rocks, and landscapes shaped by erosion. In materials science, they help examine surfaces that are rough, porous, or full of tiny pathways. The importance is practical. Many processes depend on surfaces and boundaries. A rough surface can react differently from a smooth one. A porous material can hold fluid, filter substances, or create more area for chemical reactions. A branching system can deliver or collect more efficiently than a single channel. The shape is not decoration. The shape changes what the system can do. This is the great lesson fractals teach. Form and function are often inseparable. The way something branches, folds, breaks, or roughens affects how it breathes, feeds, drains, heats, cools, grows, and survives. And because fractals appear in so many places, they also teach humility. They show that nature is not messy because it lacks order. It is messy because its order is richer than our simplest categories. The world does not always choose between smooth design and total disorder. It often lives in the middle, where patterns repeat imperfectly, where roughness has structure, where the same kind of logic can appear in air, water, wood, flesh, and stone. This does not mean everything is secretly the same. A lung is not a river, a cloud is not a tree, but they share a family of solutions. Reach outward, divide inward, fill space, increase contact, move something through a limited body. Once you see that, the world begins to feel less like a collection of separate objects and more like a set of recurring problems solved in different materials. Breath solves one problem, water solves another. Light, air, nutrients, heat, and pressure each leave their own handwriting. Fractals are how we begin to read some of that handwriting. They remind you that complexity can be organized without being rigid, that roughness can carry information, and that beauty often comes from a balance between repetition and variation. So the next time you look at a tree against the sky, or watch clouds slowly changing shape, or imagine air moving through your lungs, do not see only scenery or biology. See architecture. See mathematics softened by matter. See a world that has learned to fold surface into space, to turn branching into life, to let the same deep idea speak through leaves, rivers, breath, and vapor. Fractals do not make nature less mysterious by describing it. They make it more intimate, because they reveal that the wild shapes around you are not careless accidents. They are working patterns, quiet strategies, living geometries. And in every breath you take, one of those hidden geometries is keeping you alive. The logistic map shows order turning into chaos. A population of imaginary rabbits can teach you something terrifying about the edge between peace and disorder. Not real rabbits in a field, not a living ecosystem with weather, disease, predators, and migration, but a tiny mathematical world where one number is fed back into the same rule again and again. This is the logistic map, one of the simplest gateways into chaos. It began as a way to think about population growth under limits. At first, the idea feels almost ordinary. A population grows when there is room and food, but it cannot grow forever because space is limited. If there are too few animals, the population can rise. If there are too many, competition pulls it down. So the rule tries to balance two forces, growth and limitation. Nothing about that sounds wild. Nothing sounds like it should create mystery. You might expect the population to settle down smoothly, as if nature were quietly finding its comfortable level. And in some cases it does. When the growth rate is gentle, the numbers climb or fall toward a stable balance, like water settling in a bowl after being disturbed. Each generation gets closer to a calm value. The system remembers its limit and behaves, but then you increase the growth rate a little, and the calm begins to tremble. The population no longer settles into one steady value. It starts bouncing between two values, high and low, as if the system cannot decide where rest belongs. Increase the rate again and the two-step rhythm splits into 4. Push it further, and 4 becomes 8, then 16. Then a pattern so fine and divided that the future starts to look unpredictable. This is not because random noise has been added. The rule is still the same kind of rule. The starting number is still just passed forward, generation after generation. but the behavior has changed from order to rhythm to chaos. That is the shock. The logistic map shows that disorder can appear without outside disorder. A clean rule can produce a future that no longer feels clean. In the 1970s, scientists such as Robert May helped show how this simple population model could reveal deep lessons about complexity. It warned that even very simple ecological models could behave unpredictably when growth and limits interact strongly enough. This mattered because people often assumed that simple causes must create simple effects. The logistic map says no. A small rule can hide a staircase into chaos. What makes this especially fascinating is the way chaos arrives. It does not always burst in suddenly like a broken machine. It often comes through a graceful sequence called period doubling. A stable point becomes two repeating points. Then the repeating pattern doubles again. Then again. The system does not lose order all at once. It fractures order into finer and finer rhythms until the pattern becomes too complex to track easily. This is one of the strangest lessons in mathematics. Chaos can have a doorway, a route, almost a choreography. It is not merely a mess, it has structure in the way it becomes messy. Even more surprising, inside the chaotic region, windows of order can reappear. The system may suddenly fall into a repeating cycle again, then break back into chaos. So the logistic map is not a simple story of order dying forever. It is more like a landscape where calm lakes, repeating waves, and stormy regions sit beside one another. Move the control number slightly, and the entire personality of the system changes. One setting gives balance, another gives a pulse, another gives apparent randomness, another gives a temporary island of order inside disorder. This is why the logistic map feels larger than its size. It is a tiny mirror of systems where feedback matters. Feedback means the next state depends on the current state. In a population, today's size affects tomorrow's growth. In a market, today's price can influence tomorrow's decisions. In a mood, today's reaction can shape tomorrow's expectation. In an ecosystem, one species' abundance can change food, competition, and survival for the next generation. Feedback loops can stabilize, but they can also amplify. They can create rhythm, overshoot, correction, and collapse. The logistic map strips this idea down to its bare bones so you can see the hidden danger. Even when you understand the rule, you may not be able to predict the distant future with confidence. In the chaotic range, two starting values that are almost identical can eventually move far apart. The first few steps may look similar, like two paths walking side by side in the fog. But after enough repetitions, the paths separate completely. This is why chaos is not the same as ordinary randomness. The system is deterministic, meaning the rule gives the next value from the previous one. If you know the starting point with perfect accuracy, the future is fixed by the rule. But in the real world, perfect accuracy is almost never available. Measurements are rounded, conditions are incomplete, tiny errors exist, and in chaotic systems, tiny uncertainties can grow until prediction breaks down. The future is not lawless, but it becomes practically unreachable. That is an important distinction. Chaos does not say science fails. It says prediction has limits even inside lawful systems. It teaches that knowing the rule is not always the same as controlling the outcome. The logistic map also changes how you think about stability. A stable system is not stable simply because it has rules. It is stable because its rules and conditions keep pulling it back toward balance. Change the strength of feedback, and stability can become oscillation. Push further, and oscillation can become chaos. This matters in ecology. If a species reproduces too aggressively under limited resources, the population may overshoot, crash, rebound, and fluctuate instead of calmly settling. In real ecosystems, of course, things are far more complicated than the logistic map. Real populations include age structure, migration, seasons, predators, disease, genetic variation, and environmental change. The logistic map is not a complete portrait of nature. It is a teaching lens. It shows one mechanism by which simple growth under limits can create complicated behavior. Its value is not that it explains everything, but that it reveals how little is needed for complexity to appear. A single repeated feedback rule can produce a whole gallery of behaviors. And there is something deeply humbling in that. You may look at the world and assume that if something becomes unpredictable, then the cause must be too large, too hidden, too mysterious, or too complicated for ordinary understanding. But sometimes unpredictability grows from a rule so simple that it almost feels childish. The mystery is not always in the ingredients. Sometimes it is in the repetition, in what happens when a process keeps meeting itself again and again. The logistic map is a reminder that time can turn simplicity into surprise. The first step may be easy, the second may be easy, but after many steps, the path can enter a region where intuition no longer holds. This is why the model feels strangely personal, even though it is just mathematics. A habit repeated can stabilize a life or trap it in cycles. A reaction repeated can become a pattern. A small overcorrection can create swings. A system pushed too hard can begin to behave in ways no one intended. Again, this does not mean human life is literally the logistic map. It means the map gives you a clean image of a broader truth. Feedback shapes futures. Repetition matters. Limits matter. Intensity matters. And sometimes the difference between calm and chaos is not a completely different world, but a small change in how strongly one part of a system responds to another. So when you hear that the logistic map shows order turning into chaos, imagine a quiet sequence of numbers standing at the edge of a cliff. At first they walk in a line, then they begin to sway, then they split into rhythms. Then the rhythms multiply until prediction dissolves into a flickering pattern. And yet beneath all of it, the rule remains. That is the beauty and the warning. The world does not need to abandon order to become unpredictable. Sometimes order, repeated deeply enough and pushed far enough, becomes the path by which chaos enters. Strange attractors reveal hidden structure. Some systems do not wander because they are lost. They wander because they are trapped inside an invisible shape. That is the strange beauty of strange attractors. They reveal that chaos is not always a collapse into total disorder, but a motion guided by hidden structure, a dance that never repeats exactly, and yet never escapes its own mysterious boundary. To understand this, imagine trying to describe the state of something that changes over time, the motion of air in a storm, the swing of a complicated mechanical system, the rhythm of a laser, the flow of fluid heated from below, or even the shifting pulse of a living heartbeat. At any single moment, the system has certain conditions: speed, position, temperature, pressure, direction, energy, or other changing qualities. Scientists can imagine these conditions as points in a kind of invisible space called phase space. This is not ordinary space like a room you can walk through. It is a map of possibilities. Every point represents one possible state of the system, and as the system changes, that point moves, drawing a path. If the system is simple and stable, the path may settle into one point, like a marble rolling to the bottom of a bowl. If it repeats in a regular cycle, the path may loop around again and again, like a clock hand returning to the same place. But in some systems, something stranger happens. The path never settles into one point. It never repeats the same loop perfectly. It keeps moving, folding, circling, returning near where it has been but not exactly where it was, as if the system remembers its past without copying it. Over time, the path begins to trace a shape. Not a solid object, not a simple loop, but a delicate, layered form that holds the motion inside it. That form is an attractor, and when it has this unpredictable, never quite repeating structure, it is called a strange attractor. The most famous example comes from Edward Lorenz, who was studying simplified equations for atmospheric convection, the movement that happens when warm fluid rises and cool fluid sinks. His model was not a full weather system, only a simplified mathematical version of certain air movements. But when its behavior was plotted, it formed a shape that looked almost like two wings or two curled loops. The motion moved around one side, then the other, never repeating exactly, never flying away into infinity, never settling down into perfect calm. The Lorenz attractor became one of the icons of chaos theory because it showed something profound. A system can be unpredictable in detail while still having a recognizable overall form. The future path may be impossible to forecast perfectly far ahead, But the range of possible behavior is not meaningless. The system has boundaries. It has tendencies. It has a hidden architecture. This is why strange attractors matter. They give shape to unpredictability. They show that chaos can be bounded. A storm may be too complicated to track perfectly far into the future, but it still follows physical constraints. A turbulent flow may twist and fold in ways that look wild, but it still carries patterns shaped by energy, friction, temperature, and motion. A heartbeat may vary from beat to beat, but healthy variation often lives within a structured range. Too rigid can be a problem. Too irregular can be a problem. Life often depends on flexible order, not mechanical repetition. Strange attractors help scientists think about systems where the path is sensitive, changing, and complex, but not arbitrary. The motion has a home, even if that home is not simple. One of the most important features of strange attractors is that they often stretch and fold the paths of a system. Imagine kneading dough. Stretch it, fold it back, stretch it again. Points that were close can separate, and points that were far can be brought near, while the whole mass stays within the same general region. In a chaotic system, something similar can happen in the space of possible states. Tiny differences can grow, but the system is also folded back into a bounded form. This stretching and folding creates the strange layered structure of the attractor. It is why the path can keep producing novelty without leaving the pattern. The system is not repeating, but it is also not free in every direction. It is creative within confinement. That idea is deeply different from ordinary disorder. If something is purely random, one moment does not carry much meaningful structure into the next. But a strange attractor belongs to a deterministic system, meaning its motion follows rules, even if those rules make long-term exact prediction extremely difficult. This creates a strange middle ground between clockwork and randomness. The system is lawful, but not easily predictable, structured, but never simple, repeating in feeling but not in exact form. And once you understand that middle ground, you begin to see why so many real systems resist simple categories. The world is rarely a perfect machine, and it is rarely pure noise. It often lives in between, where rules generate variation, where patterns guide change, where uncertainty moves inside a hidden frame. Strange attractors have been studied in many areas, including fluid dynamics, electrical circuits, chemical reactions, population models, lasers, and biological rhythms. Their value is not only visual, though their images can be hauntingly beautiful. Their value is conceptual. They let researchers see whether a changing system may have an underlying structure instead of being merely random. When data from a system forms an attractor-like pattern, it suggests that the motion may be governed by internal rules, even if those rules produce complicated behavior. This is one reason scientists look for patterns in time series data, such as measurements taken again and again over time. The question becomes, is this just noise, or is there a hidden shape behind it? Is the system drifting freely, or is it being pulled towards certain forms of behavior? That word, attractor, is important because it suggests a kind of pull. Not a physical magnet necessarily, but a tendency. A system may be drawn toward a certain range of motion because of its own rules and constraints. In life, we often know this feeling even outside mathematics. A conversation can keep circling the same emotional territory without repeating the same words. A family can fall into familiar patterns, even when every day is different. A habit can produce new situations that still somehow feel like the same old loop. Again, these human examples are not literal strange attractors in the strict scientific sense, but they help you feel the idea. A path can vary endlessly while remaining shaped by a deeper pull. The scientific lesson is sharper and more exact, but the emotional resonance is real. Hidden structure can guide motion without making it obvious. You may think you are watching chaos, when you are really watching a pattern too complex to recognize at first glance. That is why strange attractors are so powerful for the imagination. They do not erase uncertainty. They give uncertainty a body. They say, look closer because disorder may have anatomy. Look longer because motion may be drawing something. Look differently because the shape of a system may not appear in any single moment, only in the long trace of its behavior. A single point tells you almost nothing. A long path begins to reveal the form. This is a patient kind of knowledge. It asks you not to judge too quickly. It asks you to let time expose the structure. So when you hear that strange attractors reveal hidden structure, imagine a system moving through the dark with a glowing thread tied to its path. At first, you see only confusion, loops, turns, returns, escapes, near misses. But slowly, the thread thickens into a shape, and the shape tells you that the wandering was never empty. The motion had a grammar, the chaos had a boundary, the unpredictability had a home, and perhaps that is the quiet wonder. Not every disorder is meaningless. Not every unstable motion is lost, and not every path that fails to repeat is without design. Sometimes the deepest structure appears only after you stop demanding a straight line and begin watching the pattern made by everything that almost returns, almost repeats, and keeps moving. The game of life creates complexity from simple rules. A universe can be born on a blank grid, without gravity, without atoms, without sunlight, and without a single living creature inside it. That is the strange doorway opened by Conway's Game of Life, a simple mathematical creation introduced by the British mathematician John Conway and made famous in 1970 through Martin Gardner's writing in Scientific American. At first, it does not look like a universe. It looks almost childish, a flat grid of tiny squares, each square either alive or dead, dark or light, present or absent. There are no characters, no goals, no score, no player moving pieces after the beginning. In fact, it is often called a zero-player game because once you choose the starting pattern, the system runs by itself. Every new moment is created from the previous one by a few plain rules. If a living cell has too few living neighbors, it dies, as if isolated. If it has too many, it dies, as if crowded. If it has the right number, it survives. If an empty cell has exactly the right number of living neighbors, it becomes alive, as if something has been born from the pressure around it. That is all. No hidden intelligence, no secret instructions, no memory beyond the previous step. And yet, from these few rules, shapes appear that seem to blink, crawl, breathe, collide, vanish, reproduce, and build machines inside the grid. The shock is not that the rules are complicated. The shock is that they are not. The game of life teaches you that complexity can emerge not because something has been carefully designed at every level, but because local conditions can create global behavior. Each cell only responds to nearby cells. It does not know the whole pattern. It does not know whether it belongs to a small cluster, a moving object, or a structure that will keep producing new shapes forever. Still, when all the cells update together, the grid begins to feel alive in a strange, abstract way. Some patterns freeze into stable forms, like quiet islands that never change unless disturbed. These are called still lifes. A small block of cells can simply remain, generation after generation, unchanged and calm. Other patterns enter repeating cycles, flipping back and forth like tiny clocks. These are oscillators, and one of the simplest is called the blinker, a row of cells that turns from horizontal to vertical and back again. Then there are patterns that move. The most famous is the glider, a tiny arrangement of cells that seems to travel diagonally across the grid, not because any individual cell is moving, but because the pattern recreates itself slightly shifted over time. This is one of the most important things to understand. In the game of life, motion can happen without any object physically sliding. The thing that moves is a pattern, a relationship, a repeating arrangement carried forward by replacement. The cells that make up the glider at one moment are not the same cells later. The identity belongs to the form, not to the material. And once you notice that, the idea becomes much deeper than a screen of squares. In many real systems, what persists is not the exact substance, but the organization. A wave crossing water is not made of the same water molecules from beginning to end. A thought in the brain is not one fixed particle traveling through you. A melody is not one note, but a pattern in time. The game of life makes that idea visible. A pattern can have identity, direction, and behavior even when its parts are constantly changing. But the grid grows stranger still. Some patterns can produce gliders again and again. The famous Gosper glider gun, discovered in the early 1970s, was a breakthrough because it showed that the game of life could create a pattern that repeatedly emits moving patterns forever. Suddenly, the grid was not just a place where small shapes died or repeated. It could become productive. It could create an endless stream of activity from a finite starting arrangement. Then researchers discovered even more elaborate structures. Patterns that act like reflectors, patterns that delay signals, patterns that send information, patterns that can be combined to perform logical operations. Over time, it became clear that the game of life is capable of universal computation. In simple terms, if you build the right arrangement, the grid can simulate the logic of a computer. This does not mean every pattern becomes a computer, and it does not mean the game of life is conscious or magical. It means the rule system is rich enough that information can be stored, moved, transformed, and combined. A few humble birth and death rules can support computation. That is astonishing. It means a flat world of blinking squares can, in principle, carry out any computation that a general computer can, if given the right starting structure and enough space and time. This is where the game of life becomes more than a curiosity. It becomes a lesson about emergence, computation, and the limits of prediction. For many starting patterns, you can watch for a while and guess what may happen. Some parts die out, some settle, some repeat. But in general, there is no simple shortcut that tells you the full future of every possible starting pattern. You often have to run the system and see. This connects to a profound idea in computer science. Some questions about what a system will eventually do cannot be answered by a neat formula for all cases. You may ask whether a pattern will die out, grow forever, or produce a certain structure. And for complicated enough setups, the only path may be to let the process unfold. The future is hidden inside the execution. That is a powerful thought. It suggests that even when the rules are completely known, the outcome may not be easily compressed into a prediction. Knowledge of the law does not always give immediate knowledge of the story. The game of life also shows how misleading appearances can be. A small pattern may vanish quickly, like a spark in rain. Another small pattern may grow into a long, active chain of events. A messy-looking starting field may settle into silence. A carefully placed structure may release gliders like messages traveling across an empty universe. The grid teaches patience because the meaning of a pattern is not always visible at the beginning. You must watch what it becomes. This is one reason the game of life has fascinated mathematicians, programmers, artists, philosophers, and curious minds for decades. It is simple enough for a beginner to understand, but deep enough that people still explore new patterns, machines, and surprises inside it. It sits in that rare space where play becomes science. You can experiment with it like a toy, yet it points toward questions about artificial life, self-organization, information, and whether complex behavior requires complex ingredients. The answer it offers is quiet but radical, not always. Sometimes a world only needs a space, a state, a neighborhood, and a rule for what happens next. From there, the story can become larger than the rule seems to promise. But it is important not to exaggerate. The game of life is not proof that real biological life is simple, or that consciousness can be explained by a grid of squares, or that the universe literally runs on these exact rules. Real life involves chemistry, evolution, energy, reproduction, metabolism, genetic information, environments, and countless physical details. The game of life is not life itself. It is a model, a metaphor with mathematical teeth. Its value is that it strips away almost everything and still leaves enough structure for lifelike behavior to appear. It shows that some features we associate with life, persistence, movement, reproduction-like activity, interaction, growth, collapse, and organization, can arise in a world where no cell has intention. And that raises a question that does not go away easily. How much of what looks purposeful in nature comes from actual planning, and how much comes from rules unfolding through time? A bird's flight, a colony's movement, a growing embryo, a market, a language, a culture. These are not the game of life, but they share the unsettling lesson that large patterns can arise from many small interactions. The grid makes the lesson clean enough to see. It tells you that complexity is not always placed into a system from above. Sometimes it awakens from below. Sometimes the whole becomes more than the vocabulary of its parts. And perhaps that is why watching the game of life can feel strangely emotional. You are looking at lifeless squares, yet you begin to care whether a little pattern survives. You watch a glider cross empty space, and for a moment it feels like a traveler. You see a structure produce signals, and it feels like communication. Your mind reaches for meaning because the system is behaving in ways that resemble meaning. That does not make the grid alive, but it reveals something about you. You recognize life not only by substance, but by pattern. You look for persistence, motion, relation, and transformation. So when you hear that the game of life creates complexity from simple rules, imagine a dark grid waiting in silence. One pattern is placed on it. Then the rules begin to breathe. Cells vanish. Cells appear. Small shapes blink like tiny clocks. Gliders drift through emptiness. Machines form from arrangements no cell understands. And slowly, the blank grid becomes a reminder that the boundary between simplicity and wonder is thinner than it seems. Sometimes the deepest worlds are not built by adding more instructions, but by letting a few instructions run long enough to reveal what they were capable of all along. Fibonacci patterns appear in some natural growth. A sunflower does not know mathematics, yet its seeds often arrange themselves as if the plant has quietly solved a packing problem older than human counting. Look into the center of a sunflower, a pine cone, a pineapple, or the growing tip of certain plants, and you may notice spirals curling in opposite directions, one set turning left, another turning right, interwoven so tightly that the surface looks organized without looking mechanical. Count those spirals in many examples, and the numbers sometimes fall into a famous sequence. 1, 2, 3, 5, 8, 13, 21, 34, 55 and onward, where each new number is made by adding the 2 before it. This is the Fibonacci sequence, named in Europe after Leonardo of Pisa, known as Fibonacci, who introduced it in a rabbit breeding puzzle in the 13th century, though related numerical ideas were known in earlier mathematical traditions. But the important thing is not the name. The important thing is the surprise. A pattern born in arithmetic can appear in living growth, not because plants are secretly doing school mathematics, and not because every beautiful thing in nature must obey one mystical code, but because growth has constraints. A plant must place new leaves, seeds, petals, or scales in a way that uses space well. It must avoid covering its own sunlight. It must pack many units into a limited area. It must expand from a growing center without leaving too much wasted space or crowding one region too heavily. Fibonacci-like patterns can appear because they are one efficient answer to that problem. In many plants, new growth appears near a tip or center, and each new unit is placed at an angle from the previous one. If that angle is too simple, like a clean half-turn or quarter-turn, new leaves or seeds line up in repeated rows and block one another. But if the angle avoids lining up too soon, each new part can occupy a gap left by earlier parts. A famous angle often connected with this is called the golden angle, roughly a little less than half a turn, and it helps distribute new growth around a center in a balanced way. Over time, as the plant adds more and more parts, visible spirals emerge, and the numbers of those spirals often match neighboring Fibonacci numbers. The plant is not counting. The plant is growing locally, step by step, under physical and biological rules, and the pattern appears because certain arrangements are naturally good at filling space. This is one of the most important corrections to make, because Fibonacci patterns are often exaggerated online. People sometimes claim that everything in nature follows Fibonacci or the golden ratio. Every shell, every galaxy, every face, every storm, every flower. That is not true. Nature is far more diverse, messier, and more interesting than a single number. Some flowers have petal counts that match Fibonacci numbers, but many do not. Some seed heads show clear Fibonacci spirals, but others are distorted by growth conditions, genetics, damage, or environmental stress. Spiral shells may grow in logarithmic patterns, but they are not all Fibonacci objects. Galaxies have spiral arms shaped by gravity, rotation, density waves, gas, and stars, not by a plant's seed-packing logic. The real wonder is not that Fibonacci controls all nature. The real wonder is more honest and deeper. When living systems grow by adding parts one at a time under spatial constraints, Fibonacci-like patterns can naturally emerge as efficient solutions. The beauty is not mystical obedience. The beauty is usefulness becoming visible. Consider the sunflower again. Its seeds form in the central disk, each one needing space to mature. If the seeds were placed in straight lines, many gaps would remain, and the head would hold fewer seeds. If they were placed randomly, crowding and inefficiency could increase. But the spiral arrangement spreads them across the disk with remarkable density. The visible spirals are not drawn first and filled later. They emerge from the way new seeds are placed as the flower grows. Pine cones show a related effect. Their scales form spiraling rows because new scales appear around a growing axis, and the most stable arrangements often produce counts from nearby Fibonacci numbers. Pineapples can display several spiral directions across their surface, each formed by the arrangement of fruitlets. In leaf arrangement, known as phyllotaxis, similar spacing can help leaves avoid shading one another too much, allowing better access to light and air. Again, it is not perfect. Real plants are living systems, not diagrams. But the tendency appears often enough to show that mathematics can describe growth without commanding it like a ruler. This distinction matters because it changes how you see nature. Mathematics is not always a cage placed over the world. Sometimes it is a language we discover after the world has already spoken. The plant grows because of cells dividing, hormones moving, tissues expanding, genes activating, and sunlight feeding the body. The mathematics appears as a pattern in the outcome, a way to understand why the form looks the way it does. In plants, a key role is played by growth hormones, such as auxin, which help influence where new organs like leaves or flower parts form. Areas with higher or lower hormone concentrations can guide where the next growth point appears, and because existing growth affects nearby conditions, each new part influences where the next one can arise. This is a biological process, not a conscious calculation. Yet the result can resemble an elegant numerical rhythm. The Fibonacci sequence also has a special relationship to proportional growth. As the numbers get larger, neighboring Fibonacci numbers approach a steady proportion, often called the golden ratio. But here too, care is needed. The golden ratio is not a magic beauty formula stamped everywhere. Its importance in plant growth comes from the way certain proportions avoid simple repetition and help distribute points efficiently. The appeal is not that nature worships a number, but that certain ratios solve certain problems well. Nature tends to keep what works. Over generations, through growth processes and evolutionary pressure, useful arrangements can become common in particular forms. This makes Fibonacci patterns a bridge between mathematics and biology. They show how a simple numerical sequence can appear not as decoration, but as the shadow of physical growth. The same idea can be humbling for your own way of thinking. When you see a sunflower, you may first see color. Then you may see beauty. Then, if you look carefully, you see organization. And beneath that organization, you find neither a cold machine nor a supernatural code, but a living process finding efficient form through repeated local decisions. The plant does not need to understand the whole pattern for the whole pattern to appear. It only needs to keep growing according to rules shaped by chemistry, space, and survival. That is a quiet lesson about complexity itself. Large order can emerge from small placement. A pattern can be real without being planned in the human sense. Beauty can be functional without becoming less beautiful, and truth can become more powerful when we remove the exaggeration from it. Fibonacci patterns are not everywhere, and they are not proof that nature is secretly built from one perfect number. They are something better. A real example of how living growth can produce mathematical structure when matter, space, and time work together. So the next time you look at a sunflower, do not reduce it to a symbol or a slogan. Let it remain alive, See the seeds pressing outward from the center, each one placed in relation to the last, each one part of a growing body, trying to use space wisely. See the spirals not as magic, but as evidence that life can discover order without ever naming it. And maybe that is the most beautiful thought of all. Nature does not need to count in order to reveal number, does not need to speak in order to express pattern, and does not need to know mathematics in order to grow in ways that mathematics can quietly understand. Prime numbers become rarer, but never end. The farther you count, the more prime numbers begin to feel like lights thinning out along an endless road. At the beginning, they appear often enough to seem friendly. 2, 3, 5, 7, 11, 13, 17, 19. They feel close, almost familiar, like stones you can step across without much effort. But keep walking and something changes. The primes become harder to find. More and more ordinary numbers stand between them. Numbers that can be broken apart into smaller factors. Numbers with hidden internal structure. Numbers built from multiplication rather than standing alone. A prime number is simple to define. It is a whole number greater than 1 that can only be divided evenly by 1 and itself. But that small definition opens one of the deepest landscapes in mathematics. Prime numbers are the atoms of arithmetic, not because they are physical, but because every whole number can be built from them through multiplication. Take a number like 12, and it can be broken into smaller prime pieces. Take 30, and it has its own prime ingredients. No matter how large the number becomes, if it is not prime, it can be decomposed into primes, like a structure taken apart until only the basic blocks remain. This is why primes matter so much. They are not just rare numbers hiding in a list. They are the foundation beneath every composite number. And yet, unlike a neat pattern of bricks, primes do not appear in a simple repeating rhythm. You can know exactly what a prime is and still not know easily where the next one will appear. That tension is what makes them feel almost alive. They are completely defined, yet strangely unpredictable. They obey absolute rules, yet their location seems scattered. You may find 2 primes close together, like 11 and 13, or 17 and 19. Then later, you may travel through a long stretch where every number can be divided by something else. As numbers grow larger, this thinning becomes more noticeable. In a rough sense, primes become less common the farther you count. Among small numbers, primes appear frequently. Among very large numbers, the chance that a randomly chosen number is prime becomes lower. This is not a mystery in the sense of being unknown. Mathematicians have a powerful understanding of the average density of primes, especially through a result known as the prime number theorem. You do not need the formula to feel the idea. It says, in simple language, that primes thin out in a predictable average way, even though their exact positions remain irregular. That is one of the most beautiful contrasts in mathematics. Locally, primes can surprise you. Globally, they follow a broad statistical pattern. They are like stars in a galaxy. No single small patch tells the whole story, but from far away, a shape begins to appear. Still, the most astonishing truth is this: primes become rarer, but they never end. No matter how far you count, no matter how enormous the numbers become, there will always be another prime waiting somewhere beyond. This was proven more than 2,000 years ago by Euclid in one of the most elegant arguments ever made. Imagine, for a moment, that someone claims there are only finitely many primes, that if you count long enough, you will eventually reach the last one. Euclid's idea was to take all those supposed primes, multiply them together, and then add one. The new number cannot be divided evenly by any prime on the original list, because dividing it by any of them leaves a remainder. So either this new number is itself prime, or it has prime factors that were not on the original list. Either way, the original list was incomplete. There cannot be a final prime. The road does not end. This proof is not long, but it is devastating. It shows that infinity can enter through a simple door. The primes may spread out. They may hide inside enormous stretches of composite numbers, but they cannot disappear. There is no last basic building block of arithmetic. The universe of numbers keeps producing new irreducible pieces forever, and this creates a strange emotional feeling because primes are both lonely and endless. Each one stands alone, indivisible in its own way, but together they support all the other whole numbers. They are isolated, yet fundamental, sparse, yet infinite, hard to predict, yet impossible to exhaust. This is why mathematicians have studied them for centuries, and why prime numbers still hold unsolved mysteries. We know they never end, but we do not know everything about how they are arranged. For example, there are pairs of primes only 2 apart, like 11 and 13 or 17 and 19, and mathematicians strongly suspect there are infinitely many such pairs. But this has not been fully proven. That open question is known as the twin prime conjecture. There is also the famous Riemann hypothesis, one of the greatest unsolved problems in mathematics, connected to the deep pattern of how primes are distributed. These mysteries do not mean primes are chaotic in a careless way. They mean that even the most basic objects in arithmetic still contain doors we have not opened. Something as simple as divisibility leads to questions that can resist the most brilliant minds for generations. And this should make you pause, because in daily life, we often assume that simple things are shallow. A child can understand what a prime number is, so we imagine the subject must be small. But primes teach the opposite. A simple definition can contain an endless depth. A thing can be easy to name and hard to understand. The primes also touch the modern world in quiet, practical ways. Large prime numbers are used in many forms of digital security, especially in systems where multiplying large primes together is easy for a computer. But reversing the process, finding the original prime factors, can be extremely difficult when the numbers are huge. This difficulty helps protect messages, banking, online communication, and private information. So primes are not only ancient curiosities written on chalkboards, they are part of the hidden machinery of trust in the digital age. Every time information moves securely across the internet, there may be prime number thinking somewhere in the background, silently helping to guard the door. But perhaps the deeper meaning of primes is not technological. Perhaps it is philosophical. They show that the world of numbers has texture. Counting is not a smooth desert where every step feels the same. It has hidden hard points, indivisible stones, places where multiplication cannot break the number down any further. And as you move farther out, those stones become less frequent, but they never vanish. There is always another one, somewhere beyond sight. That is a powerful image. Rarity without extinction, difficulty without ending, silence with something still waiting inside it. Primes become rarer, yes, but the thinning is not death, it is distance. The further you go, the more patient you must become. You cannot demand that the next prime appear exactly when you want it. You search, you test, you wait, and eventually another one emerges from the long field of numbers, indivisible and complete. Maybe that is why primes feel so different from ordinary arithmetic. They remind you that order does not always mean obvious repetition. Something can be lawful without being easy. Something can be infinite without being crowded. Something can be foundational while appearing only occasionally. So the next time you count, imagine the primes hidden along the number line like quiet lanterns. At first they glow close together. Then the gaps widen. The darkness between them grows. But the lights do not stop. Somewhere beyond every stretch of ordinary numbers, beyond every long silence of divisibility, another prime is waiting, rare, stubborn, and unbroken, reminding you that even in the most familiar act of counting, there is an endless mystery still unfolding. Probability can defy intuition. Your instincts were built to notice movement in the bushes, not to calculate invisible chances hiding behind a closed door. That is why probability can feel so strange. It does not always agree with the way your mind wants the world to work. You expect chance to feel fair, balanced, and easy to read. But probability often behaves like a quiet teacher correcting your confidence. It shows you that what feels obvious can be wrong, what feels unlikely can be common, and what feels like a meaningful sign can sometimes be only the natural result of many opportunities. The human brain is powerful, but it did not evolve as a perfect probability machine. It evolved to react quickly, to recognize danger, to form stories, to make decisions before every detail was known. In the wild, that was useful. If a sound in the dark might be a predator, it was safer to assume danger than to wait for perfect evidence. But when you bring that same instinct into games, statistics, medicine, courts, finance, science, or everyday judgment, it can mislead you. Probability asks you to slow down and separate feeling from structure. One of the cleanest examples is the Monty Hall problem, a puzzle that has frustrated thousands of intelligent people because the right answer feels wrong at first. Imagine there are 3 doors. Behind one is a prize. Behind the other 2, nothing. You choose a door, then the host, who knows what is behind the doors, opens one of the other doors that definitely has nothing behind it. Now 2 doors remain, your original choice and the other unopened door. You are offered the chance to switch. Most people feel that it no longer matters because 2 doors remain, so the chance must be half and half. But the best choice is to switch. Your original door had only a 1 in 3 chance of being right when you picked it. The other 2 doors together had a 2 in 3 chance. When the host opens an empty door from that other side, he is not giving you random information. He is concentrating that 2 in 3 chance onto the remaining unopened door. Switching does not guarantee a win, but it wins more often over many trials. This feels strange because your mind focuses on the final picture, 2 closed doors, and forgets the history of how that picture was created. Probability often depends not only on what you see now, but on the process that brought you there. That is one reason intuition fails. It treats outcomes like snapshots, while probability treats them like stories with hidden rules. Another place where probability defies intuition is in medical testing. Imagine a disease is rare and a test is very accurate but not perfect. If you test positive, your fear may immediately tell you that you probably have the disease. But the answer depends on more than the test's accuracy. It also depends on how common the disease is in the group being tested. If very few people actually have it, then even a small false positive rate can create many positive results among people who are healthy. This does not mean the test is useless. It means a result must be interpreted with context. Doctors often think in this layered way. How likely was the condition before the test? And how much does the test result change that likelihood? Your intuition, however, wants one dramatic answer. Positive feels like yes, negative feels like no. Probability says not so fast. Evidence has weight, but its weight depends on the background. This same mistake appears in courts and investigations, where people may confuse the probability of evidence if someone is innocent with the probability that someone is innocent given the evidence. Those sound similar, but they are not the same. A rare match can be powerful, but it must still be placed inside a larger situation. How many people could have been tested? How reliable the method was? What other evidence exists? And whether the reasoning is moving in the correct direction? Probability punishes careless shortcuts because it cares about conditions. It asks, given what? Compared with what? Out of how many? Under which assumptions? These questions may sound dry, but they protect truth. Without them, people can be convinced by numbers that feel impressive, but are incomplete. Another reason probability feels unnatural is that the mind struggles with large groups. If something has only a tiny chance of happening to one person, it feels almost impossible. But if millions of people have the opportunity for it to happen, then someone experiencing it may become very likely. This is why extraordinary coincidences happen in ordinary life. You think of someone and they message you. You dream of a place and then see it mentioned the next day. You hear the same unusual word twice in 1 week. These moments feel charged with meaning because you experience them personally, one at a time, from the inside, but across a life filled with thousands of thoughts, conversations, dreams, images, videos, names, songs and encounters. Some coincidences are expected. The surprising thing is not always that a coincidence occurred. The surprising thing would be if no coincidences ever occurred. Probability does not erase the emotional beauty of these moments, but it asks you not to confuse emotional intensity with statistical impossibility. A coincidence can feel meaningful even when it does not require a hidden force. That distinction is important. Wonder does not have to become superstition. You can be amazed by chance without inventing a false cause for it. Probability also challenges your sense of streaks. In games, sports, markets, and daily luck, people often see a run of events and assume it must either continue because there is momentum or reverse because balance is due. But many chance processes do not have memory. A fair coin does not know it landed heads 5 times before. A roulette wheel does not feel pressure to correct itself. The next event is not morally responsible for the previous ones. Your mind, however, loves narrative. It sees a streak and wants a plot. It sees a pattern and wants intention. This can make randomness look less random than it is. A truly random sequence often contains clusters and streaks, because randomness does not mean perfect alternation. If heads and tails appeared in a perfectly balanced, neatly alternating order, that would actually be suspicious. Real chance is lumpy. It has patches. It has strange-looking runs. It can look like a message, because your brain is a message-making organ. This is not a weakness to be ashamed of. It is a feature that becomes dangerous only when you forget it is there. Probability teaches you to ask whether the pattern you see is stronger than what chance alone could plausibly produce. That is a careful question, and careful questions are often less exciting than instant certainty, but they are far more trustworthy. There is another famous trap called the conjunction fallacy, though you do not need the name to understand it. People often think a detailed story is more likely than a simple one because the detailed story feels more realistic. For example, if you hear about someone who is intelligent, outspoken, and deeply concerned with social issues, you may think it is more likely that she is both a bank worker and an activist than that she is simply a bank worker. The combined story feels more vivid, but in probability, adding extra conditions usually makes an event less likely, not more. Every added detail narrows the path. The story becomes richer, but the chance becomes smaller. This is one of the deepest ways probability humbles imagination. A believable story is not always a likely story. Your mind rewards coherence. Probability rewards possibility space. And those are not the same. This matters far beyond puzzles. News, rumors, conspiracy theories, marketing, personal fears, and social media narratives often become persuasive because they are detailed. They connect dots. They feel complete. But a complete feeling story can still be less likely than a simpler explanation. Probability asks you to resist the seduction of narrative when the evidence does not support it. It does not ask you to stop imagining. It asks you to notice when imagination has started pretending to be proof. And perhaps this is the deeper lesson behind all these examples. Probability is not cold because it removes meaning. It is honest because it separates meaning from likelihood. It helps you live in a world where uncertainty is not a failure, but a condition. You rarely have perfect information. You choose with partial evidence. You judge risks. You interpret signs. You decide whether to trust, wait, switch, test, invest, forgive, try again, or walk away. In all of this, intuition is useful but not enough. Feeling can alert you, but it cannot always calculate. Confidence can energize you, but it can also blind you. Probability gives you a slower kind of vision. It teaches you to ask how many chances there were for something to happen. What information was revealed? What was known before? What assumptions are hidden? And whether a vivid story is quietly narrowing the truth. So when you hear that probability can defy intuition, do not imagine that your mind is broken. Imagine that it is ancient. It was shaped for quick survival, not invisible mathematics. Probability is one of the tools that helps the ancient mind see the modern world more clearly. It does not make life certain. It does something better. It teaches you how to think inside uncertainty without being ruled by fear, coincidence, or a beautiful but misleading story. The birthday paradox feels impossible, but isn't. A room with only 23 people can hide a coincidence that feels far too large for the room itself. You look around and see a small gathering, maybe a classroom, a meeting, a dinner, a group of strangers waiting for something to begin, and your intuition says there is no way 2 people are likely to share the same birthday. After all, the year has 365 possible days. 23 people feels tiny beside that. It feels like tossing a handful of pebbles into a huge field and expecting two of them to land on the same blade of grass. But this is where the birthday paradox quietly breaks the mind's first guess. In a group of just 23 people, the chance that at least two share a birthday is a little over half, assuming birthdays are evenly spread through the year and ignoring leap day. With around 30 people, the chance becomes much higher. With around 70 people, it becomes almost certain. At first, this feels impossible because you are probably asking the wrong question in your head. You may be thinking, what are the chances someone has my birthday? That is a much smaller question. If you walk into a room and ask whether anyone matches your specific birthday, then yes, 23 people is not enough to make that very likely. But the birthday paradox is not asking whether someone matches you. It is asking whether any two people in the room match each other. And that changes everything, because the number of possible pairs grows much faster than the number of people. In a group of 23, there are many different person-to-person comparisons happening silently at once. The first person can be compared with 22 others, the second with 21 others who have not already been paired with them, then 20, then 19, and so on. When all those hidden comparisons are counted, the room contains far more chances for a match than your intuition notices. This is the core of the paradox. The people are few, but the relationships between them are many. Your eyes count heads, probability counts pairings, and those are not the same thing. To understand it gently, imagine birthdays as empty boxes, one box for each day of the year. If you place one person into a random box, nothing surprising happens. Place a second person, and there is only one possible comparison. Place a third person, and now there are 3 comparisons. Place a fourth, and there are 6. The group is still small, but the possible connections between people multiply. By the time you reach 23 people, there are enough invisible pairings that a shared birthday becomes more likely than not. The paradox feels strange because the matching is distributed across the whole group. No single person is carrying the whole chance. The coincidence can happen between the quiet person near the window and someone by the door, between two people who never speak, between any pair at all. Your mind does not naturally track all those hidden links. It sees individuals, not the web between them. This is why the birthday paradox is such a powerful lesson in probability. It teaches that likelihood is often not about how many objects there are, but how many ways those objects can interact. A small group can contain a surprisingly large number of possible connections. This same idea appears far beyond birthdays. In computer science, a related problem appears when systems create digital fingerprints, sometimes called hashes, to identify files or messages. If many items are assigned shorter identifiers, the chance that two different items accidentally receive the same identifier, a collision, can become significant much sooner than simple intuition expects. This is one reason designers of secure systems use very large spaces of possible identifiers. They are not only asking whether one specific item gets a specific label, they are guarding against any two items colliding with each other. The birthday idea also helps explain why coincidences in social life can feel more mysterious than they are. If you meet many people, live through many days, remember many names, visit many places, and notice many dates, then the number of possible connections among events becomes enormous. Some overlap is expected. That does not make the moment meaningless. It simply means that coincidence has more room to appear than your mind first imagines. But the birthday paradox also teaches caution. The famous 23-person result depends on simplified assumptions. Ordinary versions usually ignore leap day and treat birthdays as equally likely across the year. In real life, birthdays are not perfectly even. Birth rates can vary by season, culture, scheduling practices, and other social factors. That can change the exact numbers slightly, but the main lesson remains strong. Matches arrive sooner than intuition predicts because pairings grow quickly. The paradox is not a trick. It is a mirror held up to the way your mind underestimates combinations. And this matters because many real-world risks behave like this. You may look at a situation and think, there are not many people here, or there are not many attempts, or there are not many chances. while the true number of interactions is much larger than it appears. In a workplace, a small team can have many possible communication links. In a network, a modest number of devices can create many possible connections. In a rumor, a few people can generate many possible paths for information to travel. In a classroom, the number of friendships, conflicts, comparisons, and shared experiences rises faster than the number of students. The birthday paradox is simple, but it trains your mind to see the hidden growth of relationships. It tells you that the space between things can matter as much as the things themselves. That is why the paradox feels almost philosophical. You enter the room thinking each person is separate, each birthday standing alone. Then probability reveals an invisible web connecting everyone to everyone else. The surprise is not inside one person, it is between them. The match appears because the room is not just a collection of individuals, it is a network of possible pairings. And perhaps this is why the idea stays with you after the numbers are explained. It changes the way you look at small groups. It changes the way you think about chance. It reminds you that your intuition often measures the visible surface, while mathematics measures the hidden structure underneath. A room may look ordinary, but inside it are quiet possibilities crossing in every direction. Most never become visible. One does. Two people laugh and say, "Wait, that's my birthday too." And suddenly the room feels touched by something unlikely. But it was not as unlikely as it felt. It was waiting in the web all along. So the next time a coincidence seems too strange to be real, pause before calling it impossible. Ask how many possible pairings existed before that one appeared. Ask how many unnoticed chances surrounded the moment. The birthday paradox does not make wonder disappear. It makes wonder more precise. It shows that the world can surprise you not by breaking probability, but by following it more deeply than your intuition can see. Networks can suddenly become connected. A network can sit in scattered pieces for a long time, almost disconnected, almost silent, and then with a few added links, suddenly become one vast connected body. This is one of the strangest truths in network science. Connection does not always grow smoothly in the way your intuition expects. You may imagine that if you keep adding roads between towns, friendships between people, wires between devices, or links between websites, the system slowly becomes more connected step by step, like filling a glass with water. But many networks behave more like ice cracking across a frozen lake. For a while, the cracks remain local, separate, and limited. Then one more crack touches another, and suddenly a path runs across the whole surface. In mathematics, this sudden shift is often called a phase transition. The phrase sounds like physics, because it is used for changes like water becoming steam, or liquid becoming ice. But networks can have their own kind of phase transition too. A collection of isolated points can cross a hidden threshold, where small clusters merge into a giant connected component, a large web where most points can be reached from most others through some chain of links. Before that threshold, the network feels fragmented. After it, it feels alive with pathways. The surprising part is that the change can happen very quickly, not because every point connects to every other point, and not because the network becomes dense like a solid wall, but because enough bridges appear in the right places to let separate islands become one continent. Imagine a group of villages scattered across a landscape. At first, each village has a few local roads. People can move inside their own region, but not easily beyond it. Then a road appears between two regions, then another. Then a bridge crosses a river, then a highway links two distant areas. For a long time, each new road seems useful but local. Then suddenly the map changes character. You can travel from almost anywhere to almost anywhere else, not directly, but through a chain of connections. The network has crossed from fragments into reachability. This idea was studied deeply in random graph theory, especially through the work of Paul Erdos and Alfred Régnier, who explored what happens when links are added at random between points. Their models showed that networks can suddenly develop large-scale connectedness when the average number of links per point passes a critical level. You do not need the technical details to feel the result. It means that a system can look broken into small pieces. Then, after a surprisingly small number of additional connections, contain a giant connected structure. That giant structure is not planned like a city blueprint. It emerges from enough local links combining into global reach. This matters because the modern world is made of networks. The internet is a network of machines and servers. Social life is a network of relationships. Transportation is a network of roads, airports, train lines, and shipping routes. The brain is a network of neurons and connections. The economy is a network of buyers, sellers, banks, supply chains, contracts, and trust. Disease spreads through networks of contact. Ideas spread through networks of attention. Power grids, food systems, ecosystems, and communication platforms all depend on connection. And in each case, a small change in connectivity can have enormous consequences. When a network is below the threshold, things stay local. A rumor dies inside one group. A computer virus infects only a few machines. A disease outbreak burns out before traveling widely. A small business remains isolated from larger markets. But when the network becomes connected enough, movement becomes easier. A rumor jumps communities. A virus finds new paths. A disease reaches distant places. A product spreads quickly. A failure in one part of a supply chain reaches another. Connectivity is powerful because it creates access, but access is double-edged. The same links that let help travel can let harm travel. The same network that spreads knowledge can spread misinformation. The same transportation system that connects families and trade can connect outbreaks. The same financial network that moves investment can transmit crisis. This is the hidden bargain of connection. When everything can reach everything else, nothing remains purely local. The world becomes more efficient, but also more vulnerable. Network science helps explain why. It asks not only how many parts exist, but how they are linked. A network with many points can still be weakly connected if the links are isolated. A smaller network can be surprisingly powerful if it has bridges between groups. Some links matter more than others, because they connect clusters that would otherwise remain separate. These are often called bridge ties in social networks. A person who belongs to two different communities can carry information between them. A road joining two regions can reshape trade. A single undersea cable can carry enormous amounts of communication. A connector does not have to be large to be important. Its importance comes from position. This is one of the most useful lessons networks teach. Influence is not only about how many connections something has, but where those connections sit. A highly connected person inside one closed circle may reach fewer new worlds than a person with modest connections across several circles. A city that connects regions can matter more than its size alone suggests. A weak link between communities can become the doorway through which new information enters. This is why sudden connection often depends on bridges, not just volume. The whole system changes when separated clusters discover paths between them. You can see this in social life. Two friend groups may remain separate for years. Then one shared event, one introduction, one collaboration joins them. Suddenly, information, relationships, opportunities, and conflicts can travel across both groups. You can see it in science too. Different fields may develop separately until a concept from one field connects to another, and suddenly a new discipline forms. Biology meets computing, physics meets finance, mathematics meets medicine. The bridge creates a new landscape of thought. And sometimes the change is not immediately visible. A network may be close to the threshold without anyone realizing it. Each added link feels minor until the system tips. This is why sudden social movements can appear to come from nowhere, even though the connections were quietly forming underneath. It is why technologies can sit unnoticed for years and then spread rapidly once enough people, platforms, and incentives align. It is why markets can shift quickly after long periods of slow change. Beneath the visible event, the network may have been preparing. The final link is not the whole cause. It is the last touch on a system already near transformation. That is an important distinction. When networks suddenly connect, we often give too much credit to the final trigger and forget the hidden build-up. The match matters, but only because the wood was dry. The bridge matters, but only because the islands were ready to join. This idea also changes how you think about loneliness, opportunity, and knowledge. A person can be talented yet isolated if they are not connected to the right networks. An idea can be brilliant yet invisible if it cannot travel. A community can be strong internally, but cut off from resources if it lacks bridges outward. Connection is not merely decoration around life. It is often the channel through which possibility moves. But connection must be shaped carefully. More links are not always better. Too few links create isolation. Too many uncontrolled links can create overload, instability, and rapid spread of damage. A healthy network often needs balance. Enough connection to share resources and information. Enough separation to prevent every shock from becoming universal. Fire breaks in forests, circuit breakers in power systems, quarantines in public health, modular design in engineering, and boundaries in personal life all reflect the same wisdom. Sometimes a system survives not by connecting everything, but by knowing where connection should pause. That is the quiet maturity of network thinking. It does not worship connection blindly. It studies the pattern of connection. Who is linked to whom? Which clusters are isolated? Where are the bridges? What happens if one hub fails? What spreads easily? What remains protected? These questions reveal the hidden architecture beneath the visible world. So when you hear that networks can suddenly become connected, imagine darkness filled with scattered points. At first, each point glows alone or in small groups. Then lines begin to appear between them. Most lines seem ordinary. A few become bridges. The clusters grow. The gaps shrink. And then, almost suddenly, there is a path across the whole field. What looked like separate lights becomes a constellation. What looked like fragments becomes a system. And maybe the deeper lesson is this. Connection is not just the presence of links, but the moment when links become pathways. A world can change not only because something new appears, but because what was already there finally becomes connected enough to move together. Small world networks make distant people close. Two strangers on opposite sides of the world can feel impossibly distant until you realize they may be connected through only a handful of human links. One person knows a teacher, the teacher knows a doctor, the doctor studied with someone who moved abroad. That person works with someone whose cousin knows the stranger. And suddenly the planet no longer feels like a vast empty distance, but like a folded fabric, where faraway points can touch through hidden lines of relationship. This is the strange idea behind small world networks. Systems where most connections are local and familiar, yet a few longer connections dramatically shrink the distance between everyone. At first, this feels almost unbelievable. The world has billions of people. Cities are enormous. Cultures are separate. Languages divide us. Lives seem sealed inside neighborhoods, jobs, families, and personal histories. But when relationships are viewed as a network, distance changes meaning. Physical distance is not the same as social distance. Someone can live thousands of miles away and still be close to you through a short chain of acquaintances, while someone in the same city can be socially unreachable if no path connects your circles. This idea became famous through the phrase 6 degrees of separation, often associated with psychologist Stanley Milgram's small world experiments in the 1960s, where people tried to send messages to a target person through acquaintances. The experiments were imperfect, and many messages never arrived, so the story should not be treated as a perfect universal law. But the deeper insight survived. Human social networks are often far more connected than they look from inside one person's life. Later, mathematicians and network scientists, including Duncan Watts and Stephen Strogatz, studied how this can happen. Their small world model showed that a network can have two qualities at once that seem almost opposite. First, it can be highly clustered, meaning your friends often know each other, your co-workers often know each other, your family members know each other, your local community forms tight circles. Second, it can still have short paths between distant parts of the system, because a few connections reach outside the local cluster. Those outside links act like shortcuts. Without them, information would have to crawl slowly from circle to circle, like a traveler moving through every village on a long road. With them, the journey can suddenly jump across the map. Imagine a neighborhood where everyone mostly talks to nearby neighbors. News moves, but slowly and mostly within the same streets. Now imagine a few residents have friends in other cities, other countries, other professions, other social worlds. Those few connections change everything. They do not need to be many. They only need to cross distance. A single acquaintance outside your usual environment can expose you to a job, an idea, a culture, a warning, a scientific paper, a piece of music, or a way of living you would never have reached through your closest circle alone. This is why acquaintances can sometimes be surprisingly powerful. Your closest friends often know much of what you already know because they live near your world. A weaker connection, someone you do not see every day, may connect you to a completely different world. Sociologist Mark Granovetter famously called attention to the strength of weak ties, showing that weaker social connections can be important for spreading information, especially opportunities like jobs. This does not mean close relationships are less valuable. Close relationships give trust, depth, care, and emotional safety. But weaker ties often give reach. They open doors into rooms your inner circle may not even know exist. That is the small world effect in human terms. Intimacy gives warmth, but shortcuts give range. You can also see small world structure beyond friendship. The brain, for example, is often studied as a network where regions are locally connected, but also linked through longer communication pathways. A brain that had only local connections might be efficient for small neighborhoods of processing, but poor at integrating vision, memory, emotion, attention, and decision-making. A brain with only random long-distance connections might be wasteful and unstable. The balance matters. Local clustering allows specialized processing. Longer connections help separate systems coordinate. In this sense, small world organization may help explain how complex systems can be both efficient and integrated. The same general idea appears in transportation, online platforms, scientific collaboration, and even the spread of ideas. Researchers often work in specialized fields, reading similar papers and attending similar conferences, but a connection between two distant fields can create a new discipline. A biologist learns from computer science. A mathematician influences economics. A physicist works with a neuroscientist. Suddenly, knowledge takes a shortcut. Innovation often comes not from staying inside one dense cluster, but from connecting clusters that usually think apart. This is why small world networks are not just about distance. They are about possibility. They show how a system can remain mostly local while still being globally reachable. But small world connectedness has a shadow. The same shortcuts that spread opportunity can also spread danger. A rumor, a panic, a computer virus, a financial shock, or a contagious disease can travel faster in a small world system because distant clusters are not as distant as they seem. In a world with many shortcuts, separation can be an illusion. Something that begins in one corner can reach another corner before people even understand the path it took. This is why public health, cybersecurity, and information systems all care about network structure. It is not enough to know how many connections exist. You must know where they go, how clustered they are, and which ones leap across distance. A tightly connected world can feel magical when it brings help, friendship, and knowledge. It can feel frightening when it brings instability. Small world networks are powerful because they compress distance, and compression changes consequences. The world becomes faster, smaller, more responsive, but also more exposed. This is one of the great truths of modern life. You may live in a room, in a town, in one personal routine, but your life is threaded into systems far larger than what you can see. A message from someone you barely know can change your career. A video uploaded in one country can influence emotion in another. A scientific discovery can move through researchers, journalists, teachers, creators, and classrooms until it reaches a child who will one day build on it. A disease can move through airports. A trend can move through platforms. A kindness can move through people who never learn its original source. The small world effect reminds you that distance is not always measured in miles. Sometimes it is measured in steps through a network, and some networks are folded so tightly that what feels far away is only a few steps from your life. This should make you careful, but it should also make you hopeful, because if distant people can be close through hidden paths, then isolation is not always as final as it feels. Somewhere outside your familiar circle may be a person who understands the thing no one near you understands. Somewhere beyond your routine may be an idea that changes how you see your future. Somewhere in a network you cannot see, a path may already exist between who you are and what you need next. The difficulty is that these paths are not always visible from the beginning. You often discover them by speaking, sharing, learning, asking, creating, reaching slightly beyond the familiar. That is how shortcuts are found, not by knowing the whole network, but by touching one edge of it and letting connection reveal the next edge. So when you hear that small world networks make distant people close, do not imagine the world becoming simple. Imagine it becoming secretly folded. Imagine neighborhoods inside neighborhoods, circles inside circles, with a few long threads tying far places together. Imagine a planet where separation is real but not absolute, where strangers can be closer than they appear, where a single unexpected link can turn distance into reach. And maybe the deepest lesson is this: you are not only a person moving through space, you are a point inside a living web of relationships, and sometimes the next life-changing connection is not far away at all. It is simply hidden a few human steps beyond what you can currently see. Power laws explain extreme events. The world's most violent events often look like exceptions until you discover they may belong to a pattern. A small earthquake rattles windows and disappears from the news. A larger one cracks walls. A rare giant one reshapes coastlines, collapses buildings, moves oceans, and enters history. At first, these events feel separated by emotion, the small ones ordinary, the large ones almost impossible. But in many systems, the extreme event is not an alien visitor from outside the pattern. It is the far end of the same pattern that produces the small events every day. This is where power laws become one of the most unsettling ideas in mathematics and science. A power law is a way of describing situations where small events are common, medium events are less common, and huge events are rare, but not as rare as your everyday intuition might expect. In a normal, familiar kind of variation, most things cluster around an average, and extreme values fade away very quickly. Human height is like this in a rough way. Most adults are somewhere near the middle. Very short and very tall people are less common, and someone 10 times taller than average simply does not appear. The extremes are tightly limited, but power law systems have what people often call heavy tails. That means the far extreme does not disappear as fast. The rare event remains rare, but it still has enough probability to matter. And when it arrives, it can dominate the whole story. Think of earthquakes. The Earth's crust is under constant stress, pushed and pulled by moving tectonic plates. Small slips happen often. Larger slips happen less often. Massive ruptures happen rarely, but they are part of the same stress release world. Seismologists use a relationship called the Gutenberg-Richter law to describe how earthquake frequency changes with magnitude. For each increase in magnitude level, earthquakes become much less frequent, while the energy released grows dramatically. You do not need the formula to understand the lesson. The planet produces many tiny shakes and very few giant ruptures, but those giant ruptures are not random monsters detached from the small ones. They are the extreme end of a scale. This is why extreme events can be misleading. If you live through quiet years, you may start to believe the system is gentle, but a power law world can store rare violence inside long calm. The absence of disaster for a while does not prove the absence of risk. It may only mean you are living in the long waiting space between extremes. This idea appears in avalanches too. A mountain slope can hold snow for days or weeks as wind, temperature, snowfall, and layers create unstable conditions. Many small slides may occur, but sometimes a larger collapse is triggered. In simplified models like the sandpile model, grains are dropped one by one until the pile reaches a fragile state where one tiny addition can cause a small slide or a large cascade. Real avalanches are far more complicated than a toy model, with snow crystals, slopes, weather, terrain, and human movement all playing roles. But the model captures a deep principle. In some systems, slow accumulation can create a state where events of many sizes are possible. Most releases are small. A few are enormous. The system does not need a giant trigger for a giant event. Sometimes the trigger is small, but the stored tension is large. That is a frightening and important distinction. We often search for the dramatic cause of a dramatic outcome. But power law thinking warns us that the cause we see may only be the final touch. The real story may be the hidden buildup. Forest fires offer another example, though again with caution, because real fire behavior depends on climate, vegetation, wind, moisture, human decisions, and land management. Many fires remain small, some grow large. A few become extreme events that overwhelm systems built for ordinary conditions. When landscapes accumulate dry fuel, when heat and drought intensify, when wind arrives at the wrong time, the size of possible fires can change. A spark may be small, but a connected dry landscape can turn that spark into a catastrophe. Here, power laws help you think not only about frequency, but about scale. They remind you that disaster size may not be neatly average. A few extreme fires can burn a very large share of the total area. A few extreme storms can cause a very large share of total damage. A few extreme floods can dominate decades of losses. This is not always because the world is unfair in a moral sense. It is because many natural and human systems are uneven by structure. They do not distribute impact politely. A small number of events can carry a massive portion of the consequence. This also appears in finance, where market changes often do not behave like calm textbook fluctuations. Most days may be modest. Then a crash, panic, liquidity failure, or sudden repricing can move markets violently. Financial returns are not perfectly described by one simple power law, and different models are used for different markets and timescales. But the broader lesson is real. Extreme movements can happen more often than a simple bell curve intuition would suggest. Treating the world as if extremes are nearly impossible can create dangerous confidence. Banks, investors, governments, and individuals can build systems that work beautifully during normal times and fail brutally during rare shocks. That is one of the hardest lessons of risk. The average is not the whole truth. Stability is not the same as safety. A bridge designed only for ordinary traffic may fail under rare stress. A supply chain optimized only for efficiency may break when one key link is disrupted. A community that has not seen flooding in decades may still be vulnerable if the landscape holds that possibility. Power laws teach you to look at tails, not just centers. They ask what the biggest events can do, not only what usually happens. But power laws must be used carefully. Not every extreme event follows a power law. Not every straight-looking pattern on a graph proves one. Many datasets are limited, noisy, mixed, or better described by other distributions. Scientists have become more cautious about claiming power laws because it is easy to see them where they do not truly exist. A responsible explanation must say this clearly. Power laws are powerful when they genuinely fit the data, but they are not a magic key for every large event. They are a lens, not a religion. Their value is that they train the mind to respect systems where the largest events matter disproportionately. They challenge the comforting idea that extremes are so rare they can be ignored. In some systems, ignoring the extreme means misunderstanding the system itself. And this changes how you think about preparation. If a system has heavy-tailed risk, then planning for the average is not enough. You need resilience. You need buffers. You need ways to absorb shock. You need systems that can fail in small parts without collapsing everywhere. You need humility, because the past may not contain the largest future event. The worst earthquake in a region's recorded history may not be the worst physically possible. The largest wildfire so far may not be the largest under a changing climate. The biggest market crash remembered by one generation may not define the limit of financial panic. Records are not walls around reality. They are only what has happened so far. A power law mindset makes that sentence feel heavier. It reminds you that rare does not mean impossible, and unprecedented does not mean unthinkable. It also reveals why extreme events can reshape memory. Many small events may happen constantly, but one enormous event can change laws, buildings, insurance, culture, migration, and fear. A single giant earthquake can rewrite engineering codes. A single massive blackout can change how power grids are managed. A single financial crash can alter politics and personal lives for years. A single viral event can change a platform, a career, or a public conversation. The extreme becomes a kind of gravitational memory. It bends everything after it. This is why power laws feel almost philosophical. They show that the world is not always governed by the middle. Sometimes the edge matters most. Sometimes the rare event is not a footnote, but the force that defines the system. You may live most of your life in ordinary days, but history is often marked by extraordinary ones. You may make many small decisions, but a few can alter the course of everything. You may see countless quiet signals, but one rare shock can reveal weaknesses that were invisible before. Again, life is not literally a power law in every detail, and we should not force mathematics onto emotion too aggressively. But the lesson resonates because it is true in many domains. Impact is often uneven. Consequences not always proportional to frequency. The things that happen least often can sometimes matter most. So when you hear that power laws explain extreme events, do not imagine they make disasters predictable in a simple way. They do something subtler. They teach you to stop treating extremes as impossible just because they are rare. They show you that small events and huge events may belong to the same family, separated not by kind, but by scale. They ask you to respect hidden buildup, heavy tails, fragile connections, and the quiet arrogance of assuming tomorrow must resemble the average yesterday. And maybe the deepest lesson is this: the world does not always whisper its danger evenly. Sometimes it speaks in thousands of small murmurs, and then one enormous shout. Power laws are one way of learning to hear both. Symmetry shapes physics and biology. Symmetry is not just something your eyes find beautiful. It is one of the hidden rules that tells the universe what is allowed to happen. You may first notice symmetry in a butterfly's wings, in the left and right sides of a face, in the circular bloom of a flower, or in the quiet balance of a snowflake. But beneath that visible beauty is a much deeper idea. Symmetry means that something can change in a certain way and still remain, in an important sense, the same. Turn a perfect sphere and it looks unchanged. Walk into a room and perform the same experiment in another corner, and the laws of physics do not suddenly rewrite themselves. Wait until tomorrow and repeat a basic physical process, and nature does not decide to use a different rule simply because time has passed. This sameness through change sounds simple, almost too abstract to matter. Yet modern science has discovered that it is one of the strongest pillars holding reality together. In physics, symmetry is not decoration. It is structure. It tells scientists why certain quantities are conserved, why some processes can happen and others cannot, why particles behave the way they do, and why the universe has patterns stable enough for atoms, stars, chemistry, and life to exist. One of the most important breakthroughs came from the mathematician Emmy Noether, who showed that deep symmetries in nature are connected to conservation laws. If the laws of physics stay the same over time, energy is conserved. If the laws stay the same from place to place, momentum is conserved. If the laws stay the same when something is rotated, angular momentum is conserved. You do not need equations to feel the force of this. It means that the universe's consistency is not just a convenience. It produces real physical consequences. The fact that nature does not change its rules from one location to another is tied to the way motion behaves. The fact that experiments do not depend on some special cosmic direction is tied to the way spinning and orbiting systems preserve their motion. Symmetry becomes a kind of promise. The universe will not cheat by changing its rules behind your back. But the story becomes even stranger because physics is also shaped by broken symmetry. Sometimes the laws may allow balance, yet the actual world chooses a particular direction, state, or form. Imagine a pencil balanced perfectly on its tip. In principle, it could fall anyway. The situation is symmetric, but once it falls, one direction is chosen, and the symmetry is broken. Something like this happens in more profound ways in nature. In the early universe, certain forces may have behaved more similarly under extreme conditions. But as the universe cooled, differences emerged. In particle physics, the Higgs field is connected with a form of symmetry breaking that helps explain why many elementary particles have mass. This does not mean mass is a simple object poured into particles. It means the structure of the fields that fill space changes how particles move and interact. The deep point is that the universe is not shaped only by perfect balance, but also by the moments when balance gives way to form. Symmetry gives possibility. Symmetry breaking gives individuality. Without symmetry, the laws would be chaotic and inconsistent. Without broken symmetry, the world might remain too featureless, too uniform, too undecided to form the rich structures we know. This same tension between symmetry and broken symmetry appears in biology, but in a softer, more visible way. Many animals show bilateral symmetry, meaning the left and right sides of the body roughly mirror each other. This is not accidental. For animals that move forward through an environment, a balanced left and right side can be useful. It helps with direction, movement, sensing, and coordination. Eyes, ears, limbs, muscles, and nerves can be arranged around a body plan that has a front and back, a top and bottom, a left and right. This kind of symmetry gives the body a stable architecture for motion. A fish swimming, a bird flying, a human walking, a cat turning its head toward a sound. All depend on bodies that are organized enough for controlled movement. But biology is never perfectly symmetrical. Your face is not exactly the same on both sides. Your heart is usually not centered in the body. Your liver and stomach are arranged asymmetrically. The brain has left and right hemispheres that share structure, but can specialize in different functions. Life uses symmetry as a starting plan, then breaks it where function requires difference. During embryonic development, a living body must solve a delicate problem. It must build a mostly symmetrical form while also deciding where asymmetrical organs should go. The body must know left from right. This is not as simple as it sounds. Early in development, tiny molecular and cellular processes help establish that left-right orientation, guiding organs into their proper positions. When those processes are disrupted, rare conditions can occur where organs are mirrored or misplaced. This reveals something profound. The body's apparent natural order is not automatic. It is built, it is instructed, it is maintained by signals so small you never feel them. Yet they decide the map of your inner world before you are even aware of being alive. Symmetry also appears in biology at the molecular level. Many molecules in living systems are chiral, meaning they can exist in left-handed or right-handed forms, like your hands, similar but not superimposable. Life on Earth strongly favors particular-handedness in key molecules. Amino acids in proteins are mostly left-handed, while sugars in DNA and RNA are mostly right-handed. This molecular preference matters because shape matters in chemistry. A molecule's handedness can change how it fits into enzymes, receptors, and biological machinery. Your body is not just made of ingredients. It is made of ingredients with orientation. A mirror image version of a molecule may behave very differently in a living system. This is why symmetry in biology is not only about what a body looks like from the outside. It reaches down into the chemistry of life itself. The lock and key precision of enzymes, the twisting structure of DNA, the folding of proteins, the way drugs interact with cells, all are affected by shape and handedness. Biology is a world where geometry becomes consequence. Physics may use symmetry to describe laws and conservation, while biology uses symmetry to build bodies, organize movement, guide development, and make chemistry work. But both reveal the same deeper truth. Form is not superficial. The way something can be transformed, mirrored, rotated, repeated, or broken changes what it can do. A perfectly symmetrical body might look beautiful, but if nothing inside it were allowed to specialize, it could not function. A perfectly uniform universe might sound elegant, but if no differences emerged, there would be no stars, no atoms arranged into chemistry, no planets, no organisms, no eyes to notice symmetry at all. The world needs balance, but it also needs departures from balance. It needs sameness to create law and difference to create story. This is why symmetry feels so powerful when you begin to notice it. It is not merely visual pleasure. It is a principle that links the deepest physics to the living body. It explains why a spinning planet obeys stable rules, why particles interact according to hidden constraints, why crystals grow in ordered forms, why animals develop body plans, why your left and right sides resemble each other, and why your inner organs quietly refuse to be perfectly mirrored. Symmetry is the universe's way of creating reliability. Broken symmetry is its way of creating surprise. Together, they make a world that is stable enough to understand and varied enough to exist. So the next time you see a butterfly, a face, a shell, a flower, or even your own hands resting in front of you, do not see symmetry as only prettiness. See it as a visible trace of a deeper order. See the left and right, the repeated and the broken, the balanced and the shifted. See how nature uses sameness without becoming trapped by it. And maybe let that thought slow your mind for a moment. You are alive because the universe knows how to preserve patterns, and also because it knows when to let them break. Optimization appears in ant trails and slime mold. A trail of ants can solve a problem that would make a human planner reach for a map, a calculator, and a long afternoon of careful thinking. At first, an ant colony looks like motion without strategy. Tiny bodies crossing soil, leaves, pavement, bark, and shadow, each insect following its own small urgency. No single ant sees the whole landscape. No ant stands above the colony with a blueprint. No ant says, "This is the shortest route to the food, and this is how the entire group should move." And yet, many ant colonies can form efficient trails between nest and food through a process that looks almost like collective intelligence. The secret is not a leader, but feedback. As ants move, many species leave chemical traces called pheromones. Other ants are more likely to follow stronger pheromone trails. If a trail leads to food and ants return successfully, that route receives more traffic, which deposits more pheromone, which attracts more ants, which strengthens the route again. Longer or less useful routes may fade because pheromones evaporate, or because fewer ants reinforce them. Over time, a colony can shift from scattered exploration toward a more efficient path, not because any individual understands optimization, but because the colony's behavior amplifies useful discoveries and lets weaker possibilities disappear. Experiments with branching bridges have shown how ants can collectively favor shorter routes through pheromone reinforcement. And this idea later inspired ant colony optimization algorithms in computer science, where artificial ants search for good paths in difficult routing and planning problems. The important word is good, not perfect. Real ants are living animals in messy environments, not mathematical machines, and they do not always find the perfect path under every condition. They can be misled by strong early trails. They can get trapped in local habits. The environment can change. Food can vanish. Obstacles can appear. But the beauty of the system is that it does not need perfect knowledge to become useful. It only needs many simple agents exploring, leaving traces, and responding to traces left by others. Optimization, in this living sense, is not a cold act of calculation. It is a conversation between movement and memory. The ground remembers where ants have been through chemical marks, and the colony reads that memory with its feet. Slime mold offers an even stranger lesson, because it does something network-like without a brain at all. The organism often studied for this is Physarum polycephalum, a yellowish slime mold that can spread through a maze-like environment as it searches for food. It is not an animal with eyes and a nervous system. It is not sitting there thinking in the human sense. Yet it can grow tube-like networks that connect food sources efficiently, then thicken useful tubes and withdraw from less useful ones. In a famous 2010 study, researchers placed food sources in positions corresponding to cities around Tokyo, and Physarum formed a transport network with features comparable to the real Tokyo rail system, balancing efficiency, fault tolerance, and cost in a surprisingly effective way. That does not mean slime mold designed the Tokyo Railway, or that it understands engineering. It means its growth dynamics can explore space and adaptively reinforce efficient connections in ways that resemble principles human engineers care about: short routes, resilient links, and low construction cost. The organism grows outward, finds resources, strengthens the veins that carry nutrients well, and shrinks the ones that are less useful. Again, optimization appears not from a central mind, but from local feedback. The slime mold's body becomes both explorer and map, both question and answer. It lays itself across possibility, then edits itself according to what works. This is why ants and slime mold are so fascinating for mathematics, computer science, biology, and engineering. They reveal a form of problem solving that is distributed instead of centralized. In human planning, we often imagine intelligence as a single mind making a complete plan before action begins. But these systems show another path. Act, sense, reinforce, remove, repeat. Explore broadly, strengthen success, abandon waste. The solution is not fully known in advance. It emerges through interaction with the environment. This has inspired algorithms used for routing, scheduling, logistics, network design, and search problems, because many real-world problems are too complicated to solve by checking every possibility directly. Instead, a system may use many rough attempts, compare outcomes, and gradually lean toward better solutions. Ant colony optimization is one example of this approach. It does not copy ants perfectly, but borrows the principle of pheromone-like reinforcement. Promising paths become more attractive, while unused paths lose influence. Slime mold-inspired models have also helped researchers think about adaptive networks, because the organism can create networks that are not merely short, but also robust. Robustness matters because the shortest path is not always the best system. A single shortest road may be efficient until it fails. A transport network, a blood vessel network, an internet route, or a supply chain may need backup paths so the whole system does not collapse when one link breaks. Physarum-like networks are interesting because they can balance competing demands. Too many links waste material and energy. Too few links make the system fragile. Somewhere between those extremes is a living compromise. That word, compromise, is at the heart of optimization in the real world. Optimization does not always mean finding the absolute maximum of one thing. It often means balancing speed, cost, safety, resilience, adaptability, and energy. A perfect-looking solution on paper may fail in a changing environment. A slightly redundant network may survive disturbance better than a leaner one. An ant trail that is good today may need to change tomorrow if food moves. A slime mold tube that is useful in one condition may be withdrawn in another. Living optimization is flexible. It is not one final answer carved into stone. It is continuous adjustment. This is what makes these organisms such powerful teachers. They solve by staying responsive. They do not separate thinking from doing. Their computation, if we use that word carefully, is embodied in movement, chemistry, growth, and feedback. The trail is the calculation. The tube network is the memory. The changing body is the model. And perhaps this is why the topic feels so quietly profound. We often treat intelligence as something that must look like us. A brain, a plan, a voice, a conscious intention. But nature keeps showing forms of intelligence-like behavior that do not look human at all. A colony can make choices no single ant understands. A slime mold can build a useful network without neurons. A forest can distribute nutrients and signals through roots and fungi. Cells can organize into tissues before there is anything like thought. This does not mean everything is conscious. It means problem solving can exist in layers below consciousness. Adaptation can happen through feedback. Order can appear through repeated local adjustments. The world does not always need a commander to become organized. Sometimes it needs many small acts, each shaped by what came before. There is also a caution hidden here. Feedback systems can be powerful, but they can also amplify mistakes. Ants may follow a strong trail even if a better one exists elsewhere, because early success can become self-reinforcing. Human systems do this too. A product becomes popular because it is already visible. A road attracts development because the road exists. A platform recommends what people already click, making certain paths stronger and others invisible. The same principle that helps ants find food can also trap systems in habits. Optimization depends on exploration as well as reinforcement. If a system only follows what is already strong, it may miss better possibilities. If it explores forever without reinforcing success, it may never settle into usefulness. Life needs both curiosity and commitment, wandering and memory, openness and pruning. Ant trails and slime mold show that the best path is often discovered by moving, not by waiting for perfect certainty. They teach that intelligence can be made of traces, that bodies can compute through contact, that networks can improve by growing and withdrawing, and that sometimes the answer to a problem is not hidden in one brilliant mind, but spread across many small interactions. So when you hear that optimization appears in ant trails and slime mold, imagine the ground itself becoming a notebook, written in pheromones and living tubes. Imagine a colony thinking through footsteps. Imagine a brainless organism drawing and redrawing a transport map with its own body. And maybe let that change the way you see problem solving in your own life. You do not always need the complete route before you begin. Sometimes you explore, leave a trace of what works, strengthen the path that gives life, and gently let the wasteful paths fade. Nature has been doing this quietly for millions of years, reminding us that the shortest answer is not always the smartest one, and that sometimes wisdom is not a single flash of insight, but a living network learning where to go. Turing patterns explain natural spots and stripes. A leopard's spots and a zebra's stripes may look like artwork painted onto skin, but one of the deepest explanations begins with something far quieter: chemicals spreading, reacting and disturbing a blank surface until pattern appears. This idea sounds almost too simple for the beauty it tries to explain. You look at an animal's coat and see identity, camouflage, warning, motion, survival, and elegance. You see a tiger vanishing into tall grass, a zebra breaking its outline in a moving herd, a tropical fish covered in shifting bands, a seashell marked with delicate waves, and it feels as if nature must have drawn each line with careful intention. But in 1952, Alan Turing, the same mathematician famous for his work in computation and code breaking, proposed a strange and powerful idea in a paper about morphogenesis, the study of how biological form develops. He suggested that patterns could arise naturally from interacting substances spreading through tissue, even if the starting point was almost uniform. In other words, a surface does not always need a detailed pattern painted onto it from the beginning. Under the right conditions, the pattern can grow from instability. The clean surface becomes uneven. Small differences become stronger. Chemicals encourage or suppress one another. Areas that were once nearly identical begin to separate into zones, and those zones can become spots, stripes, rings, or waves. Today, this kind of process is often called a reaction diffusion system. The basic idea is gentle enough to imagine without equations. One substance may act like an activator, encouraging more of itself or encouraging pigment to appear. Another may act like an inhibitor, spreading farther or faster and preventing that activation nearby. If the activator strengthens locally while the inhibitor spreads more broadly, the surface can break into repeating patches. A spot may form where activation wins, while the surrounding region is kept quiet by inhibition. Stretch that process across a growing body, and the final result can become a pattern that looks designed, even though it emerged from local interactions. This is the heart of Turing's insight. Order can be born from a balance of reaction and spread. Not random paint, not a conscious blueprint, but a self-organizing process where matter follows rules and form appears. The idea is powerful because it explains how nature can create repeated patterns without specifying every stripe and every dot individually. A genetic program does not necessarily need to say, "Put this spot exactly here, this stripe exactly there." Instead, genes may help create the conditions, cells, signals, and timing that allow a pattern-forming process to unfold. That distinction matters. Genes are still essential. Development is still biological. Evolution still shapes what patterns survive. But the visible design may be generated by a dynamic system, not by a pixel-by-pixel instruction manual. This is why Turing patterns feel so fascinating. They sit between biology and mathematics, between life and geometry, between chemical reality and visual beauty. They show how a living body can use simple physical principles to create rich surfaces. Scientists have found Turing-like mechanisms or reaction diffusion ideas useful in studying many patterns, including pigmentation in fish, spacing of hair follicles and feathers, certain skin markings, and even some structures in developing tissues. In zebrafish, for example, interactions among pigment cells help create stripes. And while the real biology is more complex than Turing's original two-chemical model, the broader principle of local activation and longer-range inhibition remains deeply relevant. In some fish, stripes can even change or regenerate after disturbance, showing that the pattern is not merely a static painting but a living arrangement maintained by cellular interaction. This is one of the most beautiful parts of the story. A pattern can be stable yet alive. It can hold its identity while still being produced by ongoing processes underneath. Animal patterns also depend on the shape and growth of the body. The same pattern-forming rules can look different on a small surface than on a large one. A narrow region may produce stripes because there is not enough room for spots to spread in all directions. A broader region may allow spots or labyrinth-like markings. As an animal grows, the pattern may stretch, split, sharpen, fade, or reorganize. This helps explain why markings often follow body contours instead of behaving like flat wallpaper. A stripe on a tail, a spot on a flank, a band around a fish, or a patch on a shell is shaped by geometry, timing, growth rate, cell movement, and chemical signaling. The body is not a passive canvas. It is part of the pattern-making system. Seashells offer another haunting example, though not always through the exact same mechanisms as animal skin. Many shell patterns are produced at the growing edge of the shell, where pigment-producing activity changes over time. As the shell grows, that edge leaves a record behind, like a moving pen writing history onto calcium carbonate. The patterns can become bands, zigzags, flames, dots, and waves, depending on how pigment activity starts, stops, spreads, and interacts. The shell does not repaint itself later. It records the dynamics of growth as it happens. That means the markings on a shell are not only decoration, they are time made visible. They are a fossil of a living process, preserved as a pattern. But it is important not to exaggerate. Not every spot or stripe in nature is a Turing pattern. Some markings come from direct genetic instructions, some from cell migration, some from environmental effects, some from sexual selection, camouflage, warning signals, or developmental constraints that do not fit a simple reaction diffusion story. A zebra's stripes, for example, are still studied and debated in terms of their functions, with ideas including protection from biting flies, temperature effects, social recognition, and visual confusion. The pattern's origin and the pattern's purpose are not always the same question. A process may explain how stripes form, while evolution explains why such stripes may have been favored. The honest truth is richer than a single explanation. Nature often layers mechanisms. Chemistry creates possibilities. Genes guide conditions. Cells interpret signals. Growth changes the canvas. Selection filters outcomes. The final animal standing before you is the result of all these levels speaking together. Turing's genius was not that he explained every natural pattern completely. It was that he showed how pattern could arise spontaneously from a nearly featureless beginning, using ordinary physical and chemical principles. That changed how scientists thought about form. It suggested that life does not always build beauty by drawing it directly. Sometimes life sets up the conditions and lets pattern emerge. This idea reaches beyond animals. Similar mathematical ideas have been used to think about vegetation patterns in dry landscapes, where plants and water interact in ways that can produce bands, spots, or gaps across the land. In some environments, plants help water enter the soil near their roots, while surrounding bare ground loses water more easily, creating feedback that can organize vegetation into visible patterns. Again, real ecosystems are complex, and no single model explains everything. But the repeated lesson is profound. When local growth and wider inhibition interact, space can organize itself. The world does not need to be random or manually designed to become patterned. It can become patterned because certain interactions make uniformity unstable. That phrase is worth feeling slowly. Uniformity unstable. Sometimes sameness cannot last. A tiny difference appears, and the system amplifies it. A faint chemical fluctuation becomes a spot. A slight imbalance becomes a stripe. A nearly blank field becomes a design. This changes how you see the living world. A tiger's coat is no longer just a surface. It is the visible ending of invisible developmental conversations. A fish's stripes are not only color, they are the memory of cells responding to one another. A shell is not only an object, it is a timeline of growth. A spotted animal is not merely decorated. It is carrying a map of biological self-organization on its skin. And perhaps that is why Turing patterns feel so strangely calming and unsettling at the same time. They show that beauty can arise without a painter, order without a central commander, design-like structure without a designer drawing every detail by hand. They do not remove wonder, they deepen it. They ask you to look at spots and stripes not as simple ornaments, but as evidence that nature can turn invisible rules into visible rhythm. So the next time you see the markings of an animal, do not rush past them as if they are only color. Imagine signals spreading through developing tissue, cells listening to nearby cells, inhibitors quieting one region while activators awaken another, the body growing as the pattern settles into place. Imagine a blankness that could not remain blank because the rules beneath it were quietly alive. And maybe the deepest lesson is this: nature's patterns are not always painted onto the world from above. Sometimes they rise from within, appearing when matter, growth, and time begin to speak the same hidden language. Entropy measures disorder and information. A warm cup of coffee cooling on a table is quietly demonstrating why time seems to move in only one direction. You do not watch the coffee gather heat from the room and become hotter by itself. You do not watch spilled milk leap back into the glass, steam return neatly into a kettle, or a shattered egg rebuild its shell on the kitchen floor. The world can rearrange itself in countless ways, but some rearrangements are overwhelmingly more likely than others, and the name we give to this hidden imbalance is entropy. Entropy is often described as disorder, but that word is only a rough doorway into the real idea. In physics, entropy is more deeply connected to the number of microscopic ways a system can be arranged, while still looking the same from the outside. A cup of hot coffee looks simple to you. Dark liquid, warm surface, maybe a little steam. But inside it, there are enormous numbers of molecules moving, colliding, rotating, exchanging energy, and constantly changing positions. When the coffee is hot and the surrounding air is cooler, the energy is unevenly concentrated. Over time, that energy spreads into the room. The coffee cools, the air warms by a tiny amount, and the difference between them fades. This happens not because the universe prefers mess, in a human emotional sense, but because there are far more ways for energy to be spread out than for it to remain neatly concentrated in one place. A hot cup in a cool room is a special arrangement. A slightly warmer room with a cooler cup is a much more common kind of arrangement. Entropy measures this move from special to common, from concentrated to spread, from a state that has fewer possible microscopic arrangements to one that has vastly more. That is why entropy gives us the arrow of time. The basic laws of physics at small scales often do not clearly forbid reversal, but the collective behavior of countless particles makes reversal fantastically unlikely. The molecules in a room could, in principle, all happen to move in just the right way to make heat flow back into your coffee. But the chance is so absurdly tiny that it is not something ordinary experience ever grants you. Time feels directional because the universe keeps moving from less probable arrangements toward more probable ones. Not because every object becomes visually messier every second, but because energy and matter tend to spread into more available possibilities. This is also why the messy room example, while useful, can be misleading if taken too literally. A room becomes messy because there are many more ways for clothes, books, and objects to be scattered than there are for them to be arranged in one exact clean order. But entropy is not really about moral tidiness. A pile of laundry is not thermodynamic entropy in its deepest sense. It is an analogy. The real story is written in heat, motion, probability, and hidden microscopic states. And this is where entropy begins to connect with information. If you know a room is perfectly arranged, you know a lot about where everything is. The socks are in the drawer, the books are on the shelf, the cup is on the desk. But if the room is described only as messy, there are countless possible versions of that mess. The socks could be on the chair, the floor, the bed, under the table, behind the door. The same visible label can hide many possible details. In physics, when many microscopic arrangements produce the same large-scale appearance, your missing information increases. You know the big picture, but not the exact microscopic story. Entropy can be understood as a measure of that hidden uncertainty. The more possible inner arrangements a system could have, the more information you would need to describe its exact state. This is why entropy and information are tied together so deeply. In the 20th century, Claude Shannon developed a mathematical theory of information for communication, asking how much uncertainty is removed when a message is received. A message that tells you something obvious carries little information. A message that surprises you carries more. If someone says the sun rose this morning, you learned almost nothing unexpected. If someone gives you the winning lottery numbers before the drawing, that message carries much more surprise, much more information, because it selects one possibility from a huge field of alternatives. Shannon's information entropy measures uncertainty in messages, how many possible messages there could have been, and how surprising the actual message is on average. This is not identical in every detail to thermodynamic entropy, but the connection is profound. Both deal with possibilities, both deal with uncertainty. Both ask in different languages how many ways something could be. In communication, entropy tells you how much information is needed to describe or transmit a source. In physics, entropy tells you how many microscopic arrangements fit a macroscopic condition. And once you see that shared structure, the universe starts to look less like a collection of objects and more like a vast bookkeeping of possibilities. A perfectly predictable signal carries little new information. A highly unpredictable signal carries more. A file with repeated simple patterns can be compressed because it contains redundancy. A file filled with truly random-looking data is harder to compress because there is no shorter pattern that captures it. This is why information theory matters in data storage, communication, encryption, compression, artificial intelligence, and modern technology. When your phone sends a photo, when a video is compressed, when a message is corrected after noise, when a search engine stores data efficiently, the logic of information entropy is somewhere nearby. It helps engineers understand how much can be removed without losing meaning, how much uncertainty a signal contains, and how much structure can be exploited. A repeated background can be described once and reused. Random static cannot be easily shortened because every part has to be specified. In that sense, entropy is not only about the universe falling apart into heat. It is also about the cost of description. How much must be known? How much can be predicted? How much uncertainty remains? The connection becomes even more striking in the famous thought experiment of Maxwell's demon. Imagine a tiny being watching molecules move between two chambers, opening and closing a little door so that faster molecules gather on one side and slower ones on the other. It seems as if the demon could create a temperature difference without spending energy, reducing entropy, and breaking the second law of thermodynamics. But the deeper analysis revealed that information is physical. The demon must measure molecules, store information, and eventually erase or process that information. Erasing information has a thermodynamic cost, a principle associated with Rolf Landauer. In simple terms, forgetting is not always free when it happens in a physical device. Information is not a ghost floating outside the world. It must be written somewhere, held by something, erased through some process, and those processes involve energy. This is one of the most mind-opening ideas in modern science. Information belongs to physics. A bit in a computer, a magnetic mark on a hard drive, a charge in a memory cell, a pattern in DNA. a neural state in the brain. All information needs a physical form. The universe does not store meaning in nothing. It stores it in arrangements. And arrangements have entropy. This is why life itself is so interesting from an entropy perspective. Living organisms maintain local order. Cells build membranes. DNA stores instructions. Proteins fold into useful shapes. Bodies regulate temperature, repair damage, and preserve structure. But life does not violate entropy. It maintains order inside itself by taking in energy and releasing waste heat and disorder into the environment. You stay alive by exchanging energy and matter with the world. Food contains concentrated chemical energy. Your body uses that energy to build, move, think, heal, and maintain internal organization, while heat and waste flow outward. Life is not a rebellion against the second law. It is a delicate local pattern sustained by a larger increase in entropy around it. That should not make life feel less miraculous. It should make it more intimate. You are not separate from thermodynamics. Every breath, every heartbeat, every thought depends on controlled flows of energy and information. Your brain, especially, is an entropy and information machine in a living sense. It reduces uncertainty about the world by sensing, predicting, remembering, and updating. You open your eyes and the brain transforms light into structured perception. You hear a sound and the brain asks what caused it. You learn from surprise because surprise means your internal model did not fully predict reality. In this way, information is not abstract for you. It is survival. It is orientation. It is the difference between noise and signal, danger and safety, hunger and food, stranger and friend. Yet the universe as a whole keeps moving toward greater entropy, at least according to our best understanding of thermodynamics. Stars burn their fuel, heat spreads, differences smooth out, useful energy becomes less available. This long-term picture can feel bleak, as if everything meaningful is destined to dissolve. But entropy is not only destruction. Entropy is also the condition that allows processes to happen. Heat flows because there are differences. Engines work because energy moves from concentrated forms toward more spread out forms. Weather, metabolism, fire, oceans, stars, and life all depend on gradients, differences that can be used before they fade. Algorithms can create surprising beauty. Beauty can begin as an instruction so plain it looks almost lifeless, and then unfold into an image, a melody, a movement, or a world that feels as if it has imagination inside it. This is the strange power of algorithms. An algorithm is simply a set of steps. Do this, then do that. Repeat here, choose there, adjust this value. Stop when a condition is reached. At first, that sounds cold, mechanical, almost the opposite of art. You may think beauty belongs to painters, musicians, architects, poets, dancers, and dreamers, not to instructions running silently inside a machine. But the deeper you look, the more that boundary begins to soften. Many forms of beauty have always depended on rules: rhythm in music, proportion in architecture, repetition in textiles, symmetry in tiles, meter in poetry, perspective in painting, choreography in dance. An algorithm is not beauty by itself, just as a brush is not a painting by itself. But under the right conditions, a rule can become a generator of surprise. In the 20th century, artists began using computers not only as tools for drawing, but as partners in creating forms that could not easily be imagined by hand. Early algorithmic artists such as Vera Molnar, Frida Naka, and Georg Nies explored how simple instructions could produce lines, grids, variations, distortions, and visual rhythms that felt both controlled and unpredictable. The machine did not feel beauty, but it could produce patterns that made humans feel something. That distinction matters. Algorithms do not need emotions to create structures that awaken emotion in us. They create by following processes, and we respond by finding form, tension, balance, surprise, and meaning in the result. Think of a digital artwork where thousands of tiny lines are placed according to a rule, but each line is slightly rotated, shifted, or interrupted. If everything were perfectly regular, the image might feel dead. If everything were completely random, it might feel meaningless. But when the algorithm holds a balance between order and variation, the image starts to breathe. Your eye follows the pattern, then notices the disturbance. It expects repetition, then meets difference. That tiny friction between predictability and surprise is where much of algorithmic beauty lives. In computer graphics, similar ideas shape the worlds you see in films and games. Mountains, clouds, fire, water, forests, textures, alien planets, cityscapes, and entire landscapes can be generated procedurally, meaning the computer creates them from rules rather than storing every detail by hand. Noise functions can give surfaces natural-looking irregularity. Growth rules can create branching shapes. Physics simulations can help cloth fall, smoke curl, waves break, or sparks scatter. None of this means the computer replaces the artist. It means the artist designs the conditions under which the machine explores possibility. The human chooses the rules, adjusts the parameters, judges the results, and decides what feels alive. Algorithmic beauty often comes from this partnership. The artist gives direction, the system gives variation, and somewhere between control and accident, something unexpected appears. This is also true in music. Algorithms can generate rhythms, harmonies, melodies, and textures by following rules about timing, pitch, repetition, and probability. Some composers use systems where a pattern transforms slowly, where notes are selected under constraints, or where the computer listens and responds. Again, the result can be beautiful, not because the machine understands longing or joy, but because structure can carry emotion when a human listener enters it. A melody is physical vibration arranged in time, yet it can make memory open. A generated pattern is only information arranged by rules, yet it can feel delicate, strange, calm, or haunting. The feeling is not inside the algorithm alone. It appears in the meeting between the pattern and the mind that perceives it. This is why algorithmic beauty raises a deep question. Where does beauty actually live? Is it in the creator's intention, in the object's structure, in the viewer's interpretation, or in the relationship between them? When Harold Cohen built Aaron, an early computer program that generated drawings, he was not just making images. He was exploring whether artistic behavior could be described as a system of choices. Aaron did not create like a human child, and it did not possess human consciousness, but it showed that some aspects of drawing could be turned into procedures. Decisions about shape, space, color, and composition. Today, generative systems are far more powerful, and the question has become even sharper. If a machine can produce something visually stunning, does that make the machine creative? Or is the creativity in the human who built the system, selected the output, shaped the dataset, wrote the prompt, trained the model, or recognized the result as meaningful? The honest answer may not be simple. Creativity may not be one single act. It may be a chain. Intention, rule, exploration, selection, interpretation. Algorithms can explore enormous spaces of possibility, but humans still bring values, context, taste, memory, and purpose. 1 million generated images are not automatically art, but one image, chosen, framed, understood, and placed into human meaning, can become part of art. Algorithms also reveal something important about surprise. We often imagine that if a process is rule-based, then its results must be boring. But rules can create results too rich to anticipate directly. A simple drawing instruction repeated with slight variation can create textures the hand would not invent. A procedural system can generate a landscape no one has ever seen before. A search algorithm can discover shapes that are efficient, elegant, or strange enough to inspire designers and engineers. In architecture and product design, computational methods can test many possible forms, sometimes producing structures that look organic because they distribute material according to stress, weight, and function. The beauty here is not only visual, it is the beauty of fitness, a form that appears because it solves a problem well. A bridge, a chair, a building facade, or a lightweight part can become beautiful because unnecessary material has been removed and the remaining structure follows forces with quiet honesty. But there is a danger too. Algorithmic beauty can become empty if it only imitates complexity without meaning. A pattern can be impressive and still shallow. A generated image can be polished and still forgettable. A system can produce endless variation and still lack direction. This is why human judgment matters. Beauty is not the same as output. More images do not automatically mean deeper art. More complexity does not automatically mean more feeling. The artist, designer, or viewer must still ask, what does this reveal? What does this make us notice? What experience does it open? What human question does it touch? Algorithms can surprise us, but surprise alone is not enough. The strongest algorithmic beauty often comes when the coldness of procedure meets the warmth of perception. When a rule produces something that feels fragile, rhythmic, alive, or impossible, and the human mind recognizes itself in the pattern. So when you hear that algorithms can create surprising beauty, do not imagine a machine stealing wonder from human hands. Imagine a new kind of instrument. A violin does not feel the music, but it can carry it. A camera does not understand a face, but it can preserve one. A computer does not dream in the way you do, but it can unfold rules into forms that make you dream differently. Algorithms show that beauty is not always born from direct control. Sometimes it is grown from constraints. Sometimes it appears when a process is allowed to search. Sometimes the most moving result is not the one the creator fully planned, but the one the creator was wise enough to recognize when it emerged. And perhaps that is the quiet lesson. Creativity is not only the act of making every detail by hand, it is also the art of choosing the right rules, listening to what they produce, and knowing when a pattern has become more than a pattern, when instruction has turned into wonder. Mathematics describes things we cannot visualize. Some truths are too large, too curved, two-dimensional, or too abstract for the human mind to picture. Yet mathematics can still hold them with astonishing precision. Your imagination was shaped by a body that moves through three-dimensional space, sees surfaces, touches objects, judges distance, and builds mental images from the world of hands, eyes, and motion. You can picture a sphere, a road, a tree, a room, a face, maybe even a planet turning in darkness. But mathematics does not stop where visualization stops. It continues into places where the inner eye goes blind. It describes four-dimensional shapes you cannot rotate in your mind, spaces that curve in ways no ordinary picture can capture, quantum states that do not behave like tiny balls, enormous datasets with thousands of directions, and abstract structures that have no simple visual form at all. This is one of the strangest powers of mathematics. It lets you reason beyond the architecture of your senses. A famous example is the four-dimensional cube, often called a tesseract. You can draw a shadow of it, just as a cube can cast a flat shadow on paper, but the drawing is not the true object. It is only a projection, a lower dimensional echo. A real four-dimensional cube is not hidden somewhere in ordinary space like a secret box behind a wall. It belongs to a kind of geometry with one more spatial direction than you can physically experience. You can describe its corners, edges, faces, and relationships mathematically, but you cannot see it directly with the same natural ease that you see a normal cube. Your brain tries to force it into familiar images, and the image collapses into a distorted symbol. Mathematics remains steady where imagination distorts. The same thing happens in modern physics. Einstein's general relativity describes gravity not as a simple pulling force in the old sense, but as the curvature of space-time. People often explain this with the image of a heavy ball bending a rubber sheet, but that picture is only a teaching aid. It shows something useful, but it also misleads, because real space-time curvature is not a two-dimensional sheet bending into a room. It is a deeper relationship between space, time, motion, and geometry. You cannot fully visualize it, but mathematics can describe how light bends near massive objects, how clocks tick differently in strong gravity, how planets orbit, and how gravitational waves travel across the universe. The equations are not decorations added after the fact. They are the language that makes accurate prediction possible when visual intuition fails. Quantum mechanics pushes this even further. The state of a quantum system is often represented in a mathematical space that is not ordinary physical space. When a physicist talks about the state of an electron or two particles becoming entangled, The full description may involve possibilities and relationships that cannot be drawn as a simple object moving along a path. Any image you use, a wave, a cloud, a spinning ball, is partial. Helpful for one idea, wrong for another. Mathematics becomes the safer guide because it does not demand that reality look like something familiar. It allows the world to be stranger than your visual imagination. This also appears outside physics. In data science and machine learning, information can have hundreds, thousands, or even millions of dimensions. A photograph, for example, can be treated as a point in an enormous space where each pixel contributes to its position. A human cannot picture such a space. You cannot imagine a 1,000-dimensional landscape the way you imagine a hill. But algorithms can still measure distances, find patterns, group similarities, and detect structures inside that space. This is how computers can recognize faces, translate languages, recommend videos, identify unusual behavior, or compress information. The machine is not seeing the space like you see a field. It is calculating relationships inside a structure too large for direct visualization. Mathematics gives access to an invisible geometry of information. This is important because human beings often trust what they can picture. If you can imagine it, it feels real. If you cannot imagine it, it feels suspicious. But many true things are not easy to picture. You cannot see radio waves with your eyes, but you use them. You cannot picture the exact arrangement of every molecule in a glass of water, but chemistry works. You cannot visualize all possible moves in a complicated system, but models can still reveal patterns. The failure of imagination is not proof that something is false. It is only proof that imagination has limits, and mathematics is one of the tools that lets the mind walk past those limits without pretending it has seen everything. Of course, mathematics is not magic. A mathematical model can be wrong if its assumptions are wrong. Numbers can be misused. Equations can describe a simplified version of reality rather than the whole living mess. But when mathematics is connected carefully to observation, experiment, and logic, it becomes a bridge into the unvisualizable. It lets scientists predict eclipses before they happen, design antennas for invisible signals, send spacecraft across space, model the spread of diseases, describe the inside of atoms, and build technologies from principles no human eye can directly see. It turns the unseen into something testable. It gives structure to what cannot be pictured. There is a quiet humility in this. Your mind is not the measure of all possible reality. The fact that you cannot form an image does not mean there is nothing there. Sometimes the world is not waiting to become a picture. Sometimes it is waiting to become a relation, a pattern, a rule, a transformation, a structure. Mathematics teaches you to think without always seeing, to understand without always imagining, to accept that truth may arrive as logic before it arrives as image. And perhaps this is why mathematics can feel both cold and spiritual at the same time. It removes the comfort of familiar pictures, but it gives you something deeper, a way to touch the shape of things your senses cannot reach. So when you hear that mathematics describes things we cannot visualize, do not imagine a failure of the human mind. Imagine an expansion of it. Imagine thought learning to move without eyes. Imagine a language that can enter dimensions you cannot picture, spaces you cannot draw, and realities that refuse to become simple images. And maybe the deepest lesson is this: the universe is not limited to what can fit inside your imagination. Sometimes the truth is not something you see in your mind. Sometimes it is something mathematics teaches you to trust before you can ever hope to picture it. The universe may be more mathematical than it feels. The universe does not feel mathematical when you are standing inside it. It feels warm, heavy, loud, painful, beautiful, frightening, and alive. You do not wake up and experience equations. You experience sunlight through curtains, the weight of your body, the taste of water, the pressure of time, the sound of traffic, the softness of a voice, the ache of memory. Reality arrives first as sensation, not calculation. And yet, beneath all of that human closeness, science keeps discovering that the world can be described with a precision so deep, it almost feels unreasonable. The motion of planets, the bending of light, the spread of heat, the vibration of atoms, the orbit of spacecraft, the rhythm of waves, the behavior of electricity, the age of distant stars, the structure of matter, even the signal inside your phone. Again and again, mathematics becomes the language that lets us predict what the senses alone could never reach. This does not mean the universe is literally made of numbers in a simple way, and it does not prove that reality is only mathematics. That would be too strong, but it does raise one of the most haunting questions in science and philosophy. Why does mathematics work so well? Why should patterns invented or discovered in the quiet space of the human mind describe things that existed billions of years before humans appeared? A curve written on paper can predict the path of a falling object. A formula about waves can help build radios, lasers, medical scanners, and communication systems. Abstract geometry, once explored as pure thought, later became essential for understanding space, gravity, and the motion of the cosmos. Complex numbers, which once seemed almost imaginary in the everyday sense, became part of the working language of quantum physics. Mathematics often feels like something we create, yet it repeatedly behaves as if we are uncovering a structure that was already there. This is the mystery. When you throw a stone, it follows a path whether or not anyone calculates it. When light passes near a massive object, it bends whether or not anyone has written the theory. When atoms absorb and emit energy, they follow strict patterns long before a scientist names them. Mathematics does not force nature to obey. It reveals that nature was already behaving in ways that can be captured by pattern, relation, quantity, and structure. But the capture is never complete in the emotional sense. An equation can describe the motion of a falling raindrop, but it does not tell you how the rain feels on your skin. It can describe sound as vibration, but not the private ache of a song returning from childhood. It can measure the energy of sunlight, but not the way a golden evening makes you suddenly quiet. This is why the universe feels less mathematical than it may be. You live at the level of experience. Mathematics works at the level of structure. The two are not enemies. They are different windows. One shows the world as felt from within. The other shows the world as organized from underneath. Consider how deeply mathematics hides in ordinary things. Music can move you emotionally, but its notes also involve ratios, frequencies, intervals, and timing. Your eyes see color as beauty, but light can be measured by wavelength and energy. Your body feels balance when you walk, but motion depends on forces, angles, feedback, muscles, nerves, and timing. A rainbow feels like wonder, but it appears because light bends, separates, and reflects inside droplets according to consistent rules. The night sky feels infinite and silent, but the position of stars, the life cycle of galaxies, and the expansion of space can be studied through measurement and mathematical models. Even uncertainty has mathematics. Even randomness can have structure. Even error can be estimated. This is not because reality is cold. It is because reality is consistent enough to be understood. If the universe changed its rules every moment, memory would fail, science would fail, life would fail. You could not learn, build, breathe, or trust tomorrow to resemble today in any useful way. The fact that mathematics works is partly the fact that the universe has regularity. But the strange part is how far that regularity goes. Mathematics does not only describe the nearby and familiar, it reaches into black holes, particle collisions, ancient cosmic light, invisible fields, and spaces no human body can enter. A spacecraft can be guided across millions of kilometers using calculations made on Earth. A prediction about a tiny particle can be tested in a machine. A signal from a distant galaxy can be translated into information about motion, composition, and time. This means the mind can touch reality at distances where the hand cannot. Mathematics becomes an extension of perception, a second kind of eyesight, one that does not replace wonder but sharpens it. Still, we must be careful. Mathematical models are not the universe itself. They are maps. Some maps are astonishingly accurate, but every map depends on assumptions, limits, and the questions we ask. Newton's laws work beautifully for many everyday motions, but they are not the final word at very high speeds, very strong gravity, or very tiny scales. General relativity and quantum mechanics each describe parts of reality with extraordinary success, yet they do not fit together perfectly in all situations. That tells us something important. Mathematics is powerful, but our mathematical descriptions can evolve. The universe may be mathematical in structure, but our understanding of that structure is unfinished. We are not reading the final book. We are learning the alphabet while standing inside the story. And perhaps that is why this idea feels so deep. Mathematics gives us confidence, but also humility. It lets us predict eclipses, design circuits, model climate, decode images, and build bridges. Yet it also leads us to mysteries that remain open. The more precisely we describe reality, the more clearly we see the edges of what we do not yet know. The universe may be mathematical, but not in a way that makes it simple. Mathematics can describe things that are too vast, too small, too fast, too curved, or too abstract for intuition. But the descriptions often open new questions rather than closing them. Why these laws? Why these constants? Why is there something rather than nothing? Why should consciousness arise in a universe whose deep structure can be written in relationships and quantities? Mathematics can guide us close to those questions, but it does not always answer the human ache inside them. And maybe that is the balance we need. If you see the universe only as feeling, you may miss the hidden order beneath it. If you see it only as mathematics, you may miss the lived miracle of being here to notice it. The world is not less beautiful because it can be measured. A flower is not less alive because its growth follows physical and biological rules. A star is not less majestic because its light can be analyzed. Your heartbeat is not less intimate because it has rhythm, pressure, electricity, and chemistry behind it. Explanation does not have to destroy wonder. Sometimes it gives wonder a deeper flaw. So when you hear that the universe may be more mathematical than it feels, do not imagine reality turning into a cold grid of numbers. Imagine instead that beneath the warmth of experience, there is a quiet architecture, a hidden music of relation and pattern that allows anything to exist consistently at all. You feel the world as touch, color, time, memory, and breath. Mathematics reveals the invisible grammar that lets those experiences unfold. And perhaps the deepest mystery is not that mathematics describes the universe, but that a small conscious being inside the universe can learn enough of that grammar to look back at the stars and understand, even slightly, how the silence is written.